Now, since Anushka took Astronomy 111, she's probably seen this video before, but you folks did not take Astronomy 111, so you have not seen this video before. It's some, oh, get away that out. It's a, I'm just going to take myself off this picture here. Stop it. Stop that. It should still be sharing this, right? It should still be showing that. Anyway, you know, you read that chapter about the sun, and this is similar material, but faux plat can have special effects behind it and stuff like that. And this will remind you of stuff you read about. And if you have any questions about the stuff you read, also for that matter, absolutely let me know as we go along here. So let's learn about the sun, shall we? We shall. All right.
The sun is a star. That's a profound statement, and one that's not really all that obvious. Those little sparks in the night sky are pretty, but don't look anything at all like the hot blazing orb that lights up our days. It was a pretty remarkable intellectual leap to understand the sun and the stars are just different flavors of the same kind of object. The only difference is that the sun is close, but the stars are terribly far away, so they're fainter. Right away, let's clear up a misconception. A lot of people say the sun is a middle-sized average star, but that's not fair. Sure, it's somewhere in the middle of the size range of stars, but the vast majority of stars are dim red dwarfs, far smaller than the sun. By size and number, the sun ranks in the top 10% of stars in the galaxy. In our solar system, it's clearly the dominant object, brighter, more massive, and more influential than anything else. But what is it? The sun is essentially a big hot ball of mostly hydrogen gas. It's 1.4 million kilometers across, more than 100 times the Earth's diameter, and big enough that well over 1 million Earths could fit inside of it. And it's massive, 300,000 times more massive than the Earth, a staggering 2 octillion tons of gas. But if we want to truly understand the sun, we have to look into its heart. At the very core of the sun, conditions are hellish. The pressure is a crushing 260 billion times the Earth's atmospheric pressure, and it's a searing 15 million degrees Celsius. Under those conditions, hydrogen is completely ionized, which means the electrons in the atoms are stripped from their protons. This makes the core a thick soup of ultra-hot subatomic particles. In fact, the protons are squeezed together so hard by the octillions of tons of mass lying on top of them that an amazing thing happens. They fuse together. Through a complicated series of steps, the hydrogen atoms fuse together to form the heavier element helium. Along the way, some of the nuclear energy stored in those atoms is released. That amount of energy is described by Einstein's famous equation E equals mc squared, which states that mass can be converted into energy and vice versa. Atoms are pretty small though, so each helium atom made in the sun's core generates only a tiny bit of energy, but a lot of helium atoms are made. A lot. Get this. Every second of every day, the sun converts 700 million tons of hydrogen into 695 million tons of helium. The missing 5 million tons, the equivalent weight of 15 Empire State Buildings, is converted into energy. And that's a lot of energy. Enough, in fact, to power a star. It's equivalent to detonating 400 billion 1 megaton nuclear bombs every single second. That's millions of times the entire nuclear arsenal of our planet, every second. And that's why, even from a distance of 150 million kilometers, the sun is so bright, you can't even look at it. Even from that distance, its heat can be felt on your skin when you stand outside. Hydrogen fusion occurs in the core of the sun. The energy released heats the gas above the core, but not quite enough to fuse hydrogen into helium. Further from the sun's center, the gas becomes less dense. And at some point, the heat pouring up from below makes the gas buoyant. It rises in the same way a hot air balloon on Earth rises. This process is called convection, and it's an efficient way of transferring heat. Huge columns of rising hot gas stretch hundreds of thousands of kilometers high, bringing the sun's internal heat to the surface. The gas then cools and sinks back down into the interior. We can actually see the tops of these columns packed together across the sun's face. Above the convecting layer is a much thinner, cooler layer very near the sun's surface called the photosphere. or literally the sphere of light. This is where the density of the material inside the sun gets thin enough that it becomes transparent. Light can shine right through it. At this point, the energy from inside the sun is free to travel into space. It's this light that we see when we look at the sun. The sun is a gas and doesn't have a solid surface, but the gas in the photosphere thins so rapidly compared to the sun's huge size that you can think of it as the sun's surface. And there's one final layer above that, the ethereally thin corona, sort of like the sun's atmosphere. It's less than 1% as dense as the photosphere, but actually much hotter. Temperatures there can reach over 1,000,000 degrees. However, it's so thinly dispersed that it's incredibly faint and can only be seen during a total eclipse or using special telescopes that block the intense light from the sun itself. The corona extends for millions of kilometers, and in a sense, it doesn't actually end. The corona merges into what's called the solar wind, a stream of subatomic particles moving away from the sun. It blows out in all directions, though mostly along the sun's equator. The speed of the wind is usually well over 1,000,000 kilometers per hour. Yes, seriously, and can reach speeds even much higher than that. When hydrogen fuses into helium in the sun's core, the energy is released in the form of light. This light immediately smacks into a subatomic particle, which absorbs it, converts a little bit of the energy into motion, and re-emits the light with a little bit less energy. The light works its way out of the sun this way, losing energy every time it encounters a particle, until eventually it gets to the surface and is free to fly away into the universe with a much lower
Good afternoon.
visible
You
light.
too, ma'am. See you. Thank you for joining us.
Some as much as 1,000,000 years. But a lot of those calculations don't model conditions inside the sun accurately. For example, they don't take into account the gas convecting for hundreds of thousands of kilometers. More modern calculations show that it takes closer to 1 or 200,000 years for the energy to work its way out. That's still a pretty long time. The light you see from the sun now got its start in the sun's core around the time Homo sapiens first appeared in Africa. The sun's surface is, to put it kindly, a mess. And the key to that mess is magnetism. I've been saying the sun is made of gas, but that's not entirely accurate. It's so hot inside the sun that electrons are stripped from their parent atoms in the gas, creating what's called a plasma, a gaseous soup of charged particles. We'll learn more about that in a later episode. But what's important now is the fact that a moving electric charge generates a magnetic field. The interior of the sun is essentially all charged particles in motion. Convection, coupled with the sun's rotation, sets up rivers or streams of plasma inside the sun, each generating and carrying its own magnetic field. When this plasma reaches the sun's surface, their magnetic fields do too. Maybe you've seen those looping arcs of magnetism around a bar magnet when it affects iron filings in a piece of paper. The solar magnetic fields are like that, except there can be zillions of them all over the sun's surface where they can interact and even get tangled up. When the plasma reaches the surface, it cools. But if the magnetic loops tangle up, they prevent the plasma from sinking back down into the sun, like a knot in a shoelace prevents it from going through the eyelet on your shoe.
video
Plasma
was
shines
against scientific
because it's hot,
research.
but as it cools, it
What's
dims. It's on
Getting
the
started with research with Dr. Harmon?
So much for not studying.
Okay, so
That's
we-
good.
Yeah, I couldn't help it. And since it's unpaid because I couldn't reserve the spot for SSRP, that's the paid internship. I'm doing this unpaid, but taking up jobs to compensate for that.
Okay, well, there you go. That's something.
Yeah.
See, it goes on the resume. That's always good.
Oh, yes. Thank you. I'll wait for you.
So, hi, Anushka.
Hello, Dr. Harmon. I'm so sorry. I didn't realize my mic was turned on.
That it was. Say hi to Mac and Julia.
Oh my goodness. This is embarrassing. Hi, Mac and Julia.
You're just decorating the audio of the video a little bit.
I am
All
very
right.
sorry.
No,
I'll
that's
turn
quite
it
all
off.
right. Quite all right. Okay. So, and now we shall continue. All righty.
Seen without using a telescope, as long as you're wearing adequate eye protection. Of course. Around the edges of sunspots, the magnetic field lines are concentrated. This can energize the plasma even further, heating it up. This creates a bright rim around sunspots called faculae, Latin for little point. The dark parts of sunspots dim the overall light from the sun, but faculae can be so intense they compensate for that and even add more light. Ironically, sunspots actually increase the energy output of the sun. Plasma on the sun's surface can flow along these magnetic loops too. This can create huge arcs of material called prominences or filaments, stretching for hundreds of thousands of kilometers across the sun. Look,
So remember, did you see during the eclipse that towards the bottom of the sun, that pink spot? Wow, that was magnetic arches.
Was a little spot that was like really close to that area. Or when we were at the projection.
Was there? Yeah, okay, yeah, uh-huh.
Because of that spot.
So it could be part of the magnetic fields associated with that, yeah. So there was a prominent arch there, and there should have been, yeah, spots in that area, most likely. So they would probably be associated with that. Now, what this is an ultraviolet image there probably, and so it's not a visible light image, so it's not quite. You're seeing the same phenomenon, but you are seeing it at a different wavelength with the naked eye there. But the pink, yeah, was a prominence, was a plasma in the chromosphere and sticking up into the corona, being supported by magnetic fields, which at the surface region would be possibly be responsible for spots being there if they were strong enough, which they probably were with something as large as that. Yep. So yes, he's talking about stuff that is very much of direct interest to us. We'll be studying it on other stars. And, you know, he mentioned that faculae, which are regions that are bright near sunspots, they can make it such that actually the extra brightness from the faculae more than makes up for the dimness of the spots. And as a result, you could actually get the sun be a bit brighter when there's spots there in integrated light, if you just take this whole brightness surface. But for star spots on other stars, which can be much larger than spots on the sun, not the case. The darkness of the spots completely dominates, and the stars look dimmer when the spots are visible for sure. There are surely other stars whose spots are similar in size to sunspots on the sun, but we wouldn't want to try to study those with this method because they would not be large enough to be able to do a very good job. So we are going to be studying spots on LO Pegasi, which are much larger compared to LO Peg than sunspots are on the sun. And it turns out it's because LO Peg's a rapid rotation produces a stronger magnetic field than exists on the sun, and therefore much larger star spots and much bigger flares and so forth too. LO Pegasi produces very powerful flares, as a matter of fact. To continue.
looking like fiery arches. We think these magnetic field lines are feeding energy from the sun's surface into the corona, which is why it's so much hotter. It's not exactly clear how this happens, but scientists are following several leads right now. This long-standing mystery may soon be solved. Magnetic fields on the sun also have a huge amount of energy stored in them. You can think of them like very tightly wound and very stiff springs. But remember, these magnetic field lines get tangled up. If conditions are right, they can actually snap, in essence creating a gigantic short circuit. When this happens, all that vast energy stored in the lines explodes outwards all at once in an event we call a solar flare. Even an average solar flare is mind-crushingly powerful. A big one can release as much as 10% of the entire sun energy output. This explosion blasts out high-energy light and launches material off the surface of the sun at high speeds, sending it into interplanetary space. Another type of solar eruption is called a coronal mass ejection, or CME. It's similar to a flare, but if a flare is like a tornado, intense and localized, a CME is like a hurricane, huge and strong. Like flares, they form when tangled magnetic field lines erupt, blasting out energy, but they occur higher off the sun's surface. Both flares and CMEs eject material into space. Billions of tons of it, in fact. This blast of debris can hit the Earth, and when it does, there can be profound effects. Our atmosphere absorbs the high-energy light, protecting us. Also, the subatomic particles are generally deflected by the Earth's magnetic field, so we're okay. But if conditions are right, the Earth's magnetic field can interact with the particles. Massive numbers are funneled down into Earth's atmosphere near the poles, causing the air to glow. This is what we call the aurora, or the northern and southern lights. Depending on the shape of the magnetic field, the auroras can form spectacular multicolored ribbons and sheets. Not all the effects are benign, though. As the magnetic fields interact, they can induce very strong currents of electricity in the Earth's crust. This can overload power grids, causing blackouts. In 1989, Quebec suffered a massive power outage from the solar storm. The very first such storm ever detected was in 1859, and it was also the most powerful ever seen. If an event like that were to happen today, it could cause worldwide blackouts and potentially be very damaging. Satellite electronics would be fried too, and we depend on those satellites for our modern civilization. In fact, in 2012, a huge storm, probably the equal of the 1859 event, blasted away from the sun in another direction, missing the Earth. Had it hit us, well, you probably wouldn't be watching this video now. We'd still be recovering. This is why studying the sun is so important. We depend on it for light and heat and the very basis of life itself, but it's entirely capable of knocking our society to its knees. Understanding it is critical to our future. The sun is the 2 octillion-ton gorilla in the room. We need to respect that. Today, you learned that the sun is a star powered by nuclear fusion in its core. Hot plasma moves inside the sun, creating magnetic fields, which in turn can create sunspots, solar flares, and coronal mass ejections. These events can generate aurorae on Earth, cause power blackouts, and damage satellites. This episode is brought to you by Squarespace. The latest version of this platform, Squarespace 7, has a completely redesigned interface, integrated with Getty Images and Google Apps, new templates, and a new feature called Cover Pages. Try Squarespace at squarespace.com and enter the code Crash Course at checkout for a special offer. Squarespace, start here, go anywhere. Crash Course Astronomy is produced in association with PBS Digital Studios. Go to their channel and find lots more awesome videos. This episode was written by me, Phil Plait. The script was edited by Blake DiFastino, and our consultant is Dr. Michelle Fowler. It was co-directed by Nicholas Jenkins and Michael Aranda, edited by Nicole Sweeney, and the graphics team is Thumb.
Yeah, there's a whole lot of crash courses on all kinds of topics, and they all are good as far as I can tell from the ones I've watched. And Crash Course Astronomy is basically Astronomy 110, 111 in video format, if you will. So we will go into a lot more mathy detail in Astrophysics 1 and 2, Astronomy 310, 311, but it's good to see certainly things at this level as well. What questions do you have, including you, Anushka? Doesn't seem to at the moment. Yes.
So what is the only difference between a coronal mass ejection and solar flare, just where it happens on the sun?
So on some level, so a coronal mass ejection, a lot more material ends up going into space. But yeah, the so-called magnetic reconnection that releases energy from the magnetic field happens higher up in a CME than it does in a flare. They're similar phenomena. They're both powered by magnetic field energy energy stored in the magnetic field being converted into other forms of energy, including kinetic energy of particles that get blasted into the interplanetary space. But a flare is a more localized event, and a coronal mass ejection takes place over a larger area because it starts higher up. Yep. What other questions do you have? If not,
That's
that's
a
good.
pretty remarkable intellectual leap to understand the sun and the stars are just different
We
flavors.
really need to fix
Or
that,
that,
because
like,
everybody seems to have this problem with Google Slides. It's hard to get it to not start playing the video again. Try to go to the next one. No, come on, I really want to go to the next slide. Where's the little thing that lets me do that? Yeah, I could, but that seems silly to have to do that. And usually there's a thing in the corner that I can choose to let me go to the next one. But I guess I will just small screen it so that I can do this. Doink. Okay. So, fun facts about the sun, basic properties of the sun. Radius, 696,000 kilometers, which is about 109 times Earth's radius. If we make a scale model where the Earth is 1 foot across, the 12-inch globe basically, then the sun would be 109 feet across. So basically, like 100 feet across, 110 feet across. this room is about 30 feet across, so 3 times the size of this room. And it would be more than 2 miles away from the 1 foot Earth on that scale. So in Astronomy 111, I always emphasize to the students, there's this common myth people have that the reason we put telescopes on mountaintops or in orbit is to get them closer to the stars. And I forget if I was mentioning that in cosmology, I probably did. Right, which is just ridiculous because, you know, the Hubble Space Telescope, for example, orbits on that same scale, like 1/3 of an inch above the surface. And the nearest star is the sun, which is more than 2 miles away. And so getting Hubble 1/3 of an inch closer to this 2 mile away sun isn't exactly giving you a better view. And other stars are at a minimum hundreds of thousands of times further away than the sun is. Anushka has a question. Does the process or the rate of the process that causes stars to generate energy affect star spots of respective stars? No, not per se. The star spots are a magnetic phenomenon that manifests itself on the surface. And so while it is true that only certain types of stars exhibit star spots, and that when we're talking about main sequence stars, ones that are fusing hydrogen into helium in their cores, it's lower mass ones that produce star spots. It's not per se because of the difference in the rate of fusion, it's because of the properties of the outer layers of the stars. So you'll see how this works out as we go along here, as a matter of fact. Let's see, sun's mass, 2 times 10 to the 30th kilograms, which is about 300,000 Earth masses. Its luminosity is 3.8 times 10 to the 26 power watts. That's a lot of light bulbs right there. Yeah, that's like, 3.8. Well, I guess it's about like 300. So a trillion's 10 to the 12. So a trillion's 10 to the 24. So this would be 380 trillion watts. That's a lot of watts. As he mentioned, that's another thing that you see so much emphasis that there are stars that are much larger than the sun. And I'm going to play a fun video in a minute, which I think I might have played in cosmology too, but I never get tired of it. It shows just how much larger some stars are than the sun. Right, that one, I'm going to play that one because I love that video. It's still the case that the sun's in the 90th percentile. The sun is more massive than 90% of the stars in the universe. So the sun's actually a big star, even though there are some stars which are much bigger than the sun. As stars go, the sun is one of the larger ones out there, if you will. Composition, 70% hydrogen, 28% helium, 2% heavier elements. Do you remember what astronomers call elements that are not hydrogen or helium? Metals, yes. So 2% metals, like carbon and oxygen, for example, right? Which sounds crazy when you say that to somebody who's taken into chemistry or is alive for that matter, right? But astronomers get used to just calling, if it ain't hydrogen and it ain't helium, it's a metal, just to give it a blanket term. I don't know who came up with that. But, I've drunk the Kool-Aid, and so it just sounds very natural to me to say that. And part of my job is to get you to drink the Kool-Aid too. So, yeah, that's right. Yes. Rotation rate, about 25 days at the equator to 30 days at the poles for the period. In other words, the sun rotates differentially because it's a big ball of plasma. It's not a solid body. So unlike the Earth, where the entire Earth is spinning once every 24 hours, different latitudes on the sun can and do have different rotation periods. And as we'll see, this is a crucial ingredient to making the sun magnetic and therefore exhibiting spots. We'll see that differential rotation plays a role in that in the sun and in other stars. Surface temperature is about 5,800 Kelvin on average. It's cooler in spots, more like, and it varies from spot to spot, but something like 4,000 to 4,300 Kelvin in the darker part of the spot. So do you remember because I didn't teach you 280, Do you remember the Stefan Boltzmann law? Which describes the relation between flux, energy per second per square meter emitted by a hot object, and surface temperature?
I don't remember, but I remember.
Yeah, so Anushka says, yes, yeah, because she took 111, and we certainly talked about it then. Flux equals sigma t to the fourth power, where sigma is the so-called Stefan Boltzmann constant, small Greek letter sigma used to represent it, and the temperature is to the fourth power. So if you double the temperature, the flux, the energy per second per square meter being emitted, doesn't double. It increases by a factor of 2 to the fourth power, or 16, in other words. So flux rises much faster than temperature does. It's to the fourth power. And so that means that to find the ratio of the umbral brightness to this photosphere's brightness, then what you would find is the ratio of 4,000 to the fourth power divided by 5,800 to the fourth power. And that means that the spots are only something like 15% or so as bright, something like that, if you run the numbers compared to the rest of the photosphere. So it's not that the spots are black. When you look at a photograph, the spots look like they're not emitting any light. It's really just that they're emitting a lot less light than the rest of the photosphere, the surface layers of the sun from which we receive most of the light. It's a contrast effect. If you set your camera exposure to show the photosphere well, the spots are underexposed, and so they look dark as a result of that. But if you could somehow magically eliminate the rest of the sun and just leave a single large sunspot shining by itself, it would be brighter than the full moon. First of all, it'd be a brilliant little pinpoint of light. It would hurt to look at. And even at the distance of the sun, that brilliant pinpoint of light would be illuminating the surface of the earth better than the full moon does. You could read by the light of a sunspot. It would be kind of an orangish color because the lower surface temperature, if you talked about Wien's law that says that the wavelength of peak emission for a black body, for a thermal emitter, is inversely proportional to the temperature. Wien's law says that the light from the spot will be ruddier, redder, if you will, shifted towards longer wavelengths than the light from the rest of the photosphere. So the spot would look kind of an orangish color given its surface temperature. And so a sunspot glowing by itself would be this brilliant orangish point of light that you could read by, is what it comes down to. So keep that in mind. It's true for our other stars too. Yes, our images, our reconstructions will make them look like dark or black or something. They're really very bright. It's just that the rest of the surface of the star is even brighter, is what it comes down to. Excuse me. Core temperature, about 15 million Kelvin. Very toasty, hot enough to fuse hydrogen into helium. Okay, let's watch that fun video that compares planets to stars, and then we'll take a break at that point. Take a 10-minute break and come back. So I think this is the one that I showed you. There's this, yeah, he's made various versions of this video, including one that goes all the way out to the, to the edge of the universe. So, well, not the edge of the universe, stop it. That's not what there's no edge to the universe. I have to turn in my cosmology card now. Yeah, out to very large scale structures. So there's this other video, this version, but this is the one where it's just stars. And he uses the theme music from the movie The Black Hole. So I think I showed you this one. Yeah,
I think you showed us both.
I think probably showed you both of them. Yeah. So right, and it's like it's spiraling around, and it's like, look, it's people and a dog. Look, it's a mountain. Look, it actually starts with like quantum foam.
Yeah.
Starts with a quantum foam. Yes, and it looks similar to the large scale structure of the universe because we think they came from the large scale structure was set by inflation, making quantum foam fluctuations, macroscopic in scale, et cetera, right? But this is the one that just deals with stars and has that fun The Black Hole is, so the Black Hole is a Disney movie from 1979, which really isn't that good. I finally watched it for the first time, but it actually was kind of controversial in 1979 because it was the first ever Disney movie that was rated anything other than G. It was their first PG movie. And they have a little bit of swearing in it, a little bit of cuss words. Now today, Disney owns all these franchises and makes movies that, you know, can be for adults only and stuff like that. But in 1979, Disney had this squeaky clean image. It makes stuff for kids and families and stuff like that. And that they had a movie where, you know, they said like damn and hell was like, oh my God, what is happening? You know, it's going to rain cats and dogs. It's the apocalypse. Disney is, you know, et cetera, et cetera. But, and the special effects, I mean, it's from the same time as Star Wars, but its special effects are not nearly as good as Star Wars. So it's kind of like, you know, but in any case, it did provide the music for this video as well, which kind of fits. It's the music that's going do 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 do. That's from the Black Hole. Yes and no. The images of, you know, like the simulated black hole in it or whatever, not nearly as good as Interstellar. And they would have known that in 1979 too. That's true. Well, and they would have known that in 79, you know, they didn't do a very good job with the black hole itself. But in any case, let's go here. It's got them spinning backwards. You spin, it's got them spinning east to west, west, east. Adorable. Get over yourself, as I always like to say. Yeah. All right, now. It's not, oh, there's a little thingy right there. Okay, so I can push to the next one. But let's take a break here before we watch this nice video about the scale of the solar system. And then did I show that in cosmology? I may or may not have. Well, we'll see. In any case, it doesn't hurt to see it again. They go out into a desert and lay out a scale model. And so I did, okay. We'll watch it again too, because you know what, it never gets old. But that'll be after we take our 10-minute break. Let's reconvene at 35 after the hour. Pause recording, Zoom recording, and enjoy cool video. No, enjoy cool video.
If you look up an image of the Earth and Moon, you're gonna get a picture where they're quite close together. Something like that. But in reality, the Earth and Moon are about that far apart. That is the Earth and the Moon to scale. Taking the same concept, but for the solar system, every single picture of the solar system that we ever encounter is not to scale. If you put the orbits to scale on a piece of paper, the planets become microscopic and you won't be able to see them. There is literally not an image that adequately shows you what it actually looks like from out there. The only way to see a scale model of the solar system is to build one. Welcome to Black Rock Desert. This is Alex. I'm Wiley. He's gonna be behind the camera. I'm gonna be probably making a lot of mistakes on camera. We have 36 hours to measure the distances, trace out the orbits, and set up a time-lapse shot from up on top of a nearby mountain. To create a scale model with an Earth only as big as this marble, you need 7 miles of empty space. So that's why we're here. Why did you guys come? I don't have a job.
This video is from 20.
At this scale, the sun is 1.5 meters, so about that big around. So we are driving right now to Mercury. We've arrived. Venus is the same size as Earth. World in my pocket somewhere. And this Mars. Got a couple of robots rolling around on that one. Once the time lapse is ready, drive each orbit with a light. Hopefully you'll be able to tell just how big they really are. To the outer planets. Jupiter. Saturn. That tiny light out there is our sun, just over a mile away. Sun's way, way out there now. So that should be headed to the solar system.
So right now, it's about 7 a.m. We just woke up right before the sun's about to rise. We are on Earth's orbit. Wiley is over there holding our sun. Cue the dramatic sunrise music.
So if we've made our model correctly, your perspective from where Earth is on the model will match your perspective from say, real Earth. So if you look back at the sun, you will see that the model sun and the real sun are exact same size. That's how you can tell that the proportions are correct. There are 24 people in the entire history of the human species, billions, who have actually seen the full circle of the Earth with their own eyes.
Following the breakfast, the astronauts went to the soup room where they donned their space.
This is my answer attempt to get to the moon.
We have a liftoff. Liftoff at 7:51.
In Earth orbit, the horizon is just slightly curved. When you head on out to the moon, the horizon slowly curves around and upon itself, and all of a sudden you're looking at something that is very strange, but is very, very familiar.
Yeah, look at that picture over there. Wow, that's crazy.
You can put your thumb up, and you can hide the Earth behind your thumb. Everything that you've ever known, all behind your thumb.
It is really beautiful. You can cry.
That's what I really wanted to try and capture. We are on a marble floating in the middle of nothing. When you sort of come face to face with that, it's staggering.
You know, I think they made this one too. I've never seen it. Let's watch it, shall we? Because why not? Well, they just wanna.
Wiley, I think we all have a pretty good grasp of what time is.
Yes.
So why are we doing this?
Every human being understands time as seconds and minutes and hours and years. But our brains are not wired to grasp how old the universe is. This is a realm of time that we cannot imagine.
All the time. How long has that clock been going? A few billion years. Why? Well, could you unwind it for? Man, are you crazy?
Best way to understand the history of the cosmos is to see a timeline that shows you the history of the cosmos. If you want to understand the age of the universe, you have to see a scale model of time. And the only way to see it is to build it. So amazing. Thanks, man. What are we doing today? With a big open space like this lake bed, you can take the years of the history of the universe, translate it into distance.
Don't check my man.
200 lights to see.
How long you sent water?
We're gonna build two models. We're gonna build a model of the history of human civilization. And then we'll build another model that shows the history of the universe. And by doing that, you can see how small we are in the history of the universe.
All right, what's the plan?
Plan, let's talk about it. In the next 10 hours, we have to lay out 800 lights, each 10 meters apart, walk 4.5 miles, probably several times in 100-degree heat.
And how are we gonna convince our friends to come and do this with us?
I think we'll have to pay them. As if this wasn't hard enough, we have to get a single shot of the whole model right at dusk when the light is dim enough so that we can see our lights, but not so dark that we can't see the landscape. We'll only have one shot.
No pressure, no pressure.
We have to get it right. Are you anticipating any running today?
I am not anticipating any running.
Why are you running?
We're getting out of daylight. Let's go faster, let's go faster. Way over there. Why do you want to do this one? I'm moving up, so kind of close. Ready for this? Ready.
One million years ago, our ancestors controlled fire. Around its warmth and safety, they become social. They cooperate to survive. They begin to cook and gain more energy from food. Over thousands of generations, their brains grow. They become we. We make tools, rituals. As Earth warms, we migrate. We make art, music, culture. We domesticate animals, then plants. We create cities, kingdoms, empires, the wheel, writing, math, monuments, religion, conquest, nations, revolution, democracy, modern science, medicine, economy, trade, industry, electricity, communication, and at last, today. But this is only the latest chapter. To see the whole story, we change our scale. The Big Bang. Time begins as the universe expands into existence. This expansion cools energy into matter. Clouds of simple atoms condense to form stars. In their cores, atoms fuse into new elements. And when fusion ends, the enriched matter returns to the cosmos. Raw material for future worlds. Over the eons, 100 billion stars gather into each galaxy. And the universe is home to 200 billion galaxies. In one, our sun and planets form. Earth cools, rain fills oceans. Atoms forged in ancient stars bond into molecules. One starts to copy itself. Life begins. It evolves to live off light. That fills our air with oxygen. Then, a powerful new kind of cell is born. From it, life evolves into endless forms. It moves onto land, grows large, but disaster strikes. Small mammals emerge into a world left to them. They evolve to be larger, smarter, stand up, and become us. We did it. Oh, man. What are you standing in front of? So what you're looking at here is a scale model of the history of the universe. And on that scale, all of human history is this big. Every person you've ever heard of existed in this last centimeter of space. And your life would be less than the width of a hair. That is your life against the history of the universe. Oh, man. That whole history just to get us here, I think it's beautiful. I think I look at this and I think, this is it, man. We have one life. We are alive for the briefest moment, but that time is a gift from the universe. It's a tiny moment, but we want a moment. It makes you think about how you want to spend your own time. What's important with the time you have?
Yes, sure. And you know, a million years is 10,000 centuries. And you know, we think of ancient Rome and it's
About $20,000 is 5 minutes. Find the most minimalist event on the planet. But we can find out if it actually does.
Nope, we won't be doing this. All right, what questions do you have? About the other one, Mishka says, the bigger challenge must have been to drive in perfect circles. I'm actually not quite sure. Yeah, how did they do that? Right, yeah. I'm not sure. Good question. I don't think they had giant strings that they, you know, were like, yeah. Right, yeah. I don't know. Not sure. All right. So as you will see when you take astrophysics, because we go over all these equations, if we want to model a star, then we can use differential equations that encapsulate the laws of physics operating inside the star. And they don't have an analytic solution that you can just write down. So you have to throw a computer at them and make numerical models. And so those four equations right there that you see, we will talk about them all in detail. Get to astronomy 310, astronomy 311. So that's something to look forward to. But in any case, so these are really they don't say this here, but these are the equations of static stellar structure, where you don't account for the fact that the star is evolving with time, that the composition is changing because of nuclear reactions in core and so forth. But the principles are essentially the same. And one of those equations, and again, you know, this, so, you know, I could take a viewpoint of, Well, we're studying star spots, and so all we need to understand are the star spots. But I think there should be a bigger context, which is why I had you read about stars in general, right? You know, let's put this all in the bigger picture. And so that's why I'm talking about stars in general before we start digging down to, okay, well, what about star spots here? One of the equations, this one right here, this is the equation of hydrostatic equilibrium. It's expressing the balance between pressure and gravity. In a star, there's the inward force of gravity and the outward push of pressure. And if the star is to be in equilibrium, not changing with time, or at least changing only very slowly with time, not expanding or collapsing, then in every layer of the star, the net outward pressure force should be equal to the net inward gravity force. And that's what that equation describes in a more, and again, we'll go over that in more detail in astrophysics, but on a more kind of qualitative level, you can think of, and it's a good analogy, the stack of guys on the left there. In other words, the guy on the bottom literally has to push harder on the guy in the middle than the guy in the middle has to push on the guy on top, because the guy on the bottom is supporting the weight of two guys above him, and the guy in the middle is only supporting the weight of one guy above him. And similarly, in the star, the deeper down, the deeper down you go, the more weight of overlying material has to be balanced, and so the pressure has to increase as you go deeper inside the star in order to balance more and more weight above you, if you will, as you go deeper inside the star. So there's a pressure gradient. Pressure increases with depth within the star, and that means that the pressure is greatest in the core. And also, it turns out that the density is greatest in the core as well. And then there's another equation in that list that is describing energy balance. And that is that if a star is to be in equilibrium, then the rate at which energy is leaving the surface of the star's luminosity. So that what would the units of luminosity be? It's energy per second leaving the star's surface, total from the surface. The luminosity we have units of watts, yeah, joules per second, right? The rate at which energy is being radiated from the surface has to be equal to the rate at which energy is being generated in the core. Because if there was a difference between those two things, if there was more energy coming out of the core than was leaving the surface, then energy would be building up inside the star. That could not be an equilibrium situation where things are not changing with time, or at least changing only very, very slowly over very long time scales. Vice versa, if more energy was leaving the surface than being generated in the core, then energy would be being depleted in the star's interior. So in order for there to be an equilibrium, for conditions within the interior to not be changing, or at least be changing only very slowly, then you have to have a balance between energy generated and energy emitted, luminosity of the star. And if it were out of equilibrium, changes would occur that brought it into equilibrium, is what it comes down to. So again, we can use these equations and feed them to a computer and numerically integrate them in order to create stellar models. And so here's one particular stellar model, and what a stellar model ends up being essentially is you can make tables or plots of pressure, density, temperature, rate of energy generation per cubic meter, and so forth within the star. So here's plots for a particular solar model. It's interesting to note that the density, notice, is much higher towards the center. The sun's center, even though it's gaseous throughout, it's much denser than lead. And it turns out that 90% of the sun's mass is within the inner 50% of its radius. All the way from halfway to the surface only contains about 10% of the sun's total mass. it's mostly concentrated towards the center, even though that's not obvious from looking. Inside the sun, and now we are starting to get to what's going to be relevant to spots and so forth. Inside the sun, we've got the core, about the inner 25% of the sun's radius is the core, where the density and temperature are high enough for nuclear reactions to occur. And then we have the radiative zone, which really the core would be part of the radiative zone as well. The radiative zone is where energy is being transported by what we call radiative diffusion. And then in the outermost layers of the sun, starting at about 20% of the way to 80% of the way to the surface, out to the surface itself, we have the convective zone where energy is transported by convection. Only stars which have outer convective zones have spots because, as I mentioned briefly before, spots are regions of strong magnetic field that suppress convection, and we'll talk about how that occurs as we go along here. But in the sun, convection, rising of hotter gas and sinking of cooler gas is the primary means by which energy is being transported towards the surface from deeper layers below. But below the convective zone, where convection is the primary means of energy transport, is the radiative zone, where energy is transported by radiative diffusion. And what that entails is the fact that we need to get energy from the core, where it's being generated, out to the surface. And for that to happen, that has to mean that the temperature of the sun increases as you go inwards. It's hotter and hotter as you go lower down. I'll pause here because Julia, you're writing, and I want to give you a chance to write what you're writing. So,
Writing.
yeah, okay. So suppose that you were beamed into the middle of the sun somewhere in the center, in the middle of the radiative zone. Well, ignoring the fact that you'd be instantly vaporized by the temperatures there before you even had time to go, keep your wing, right? Not that you were falling asleep. Well, imagine you're in there, okay? You can't see forever. The material has an opacity to it, so you can only see to a certain distance in any given direction. But if you are right here on the dashed line and are looking towards the center of the sun, looking towards the core, you are looking towards layers that are hotter and therefore giving off more energy per second, per square meter, if you will, than the layer that you're at. And similarly, if you look towards the surface, you're looking towards layers that are, or material that is cooler than your location, is giving off less light per second, light energy per second than your location. And so that means that while it would be incredibly bright no matter which direction you looked, it would be a little bit brighter towards the center than it is towards the surface. And that means that while there are a tremendous number of photons and a tremendous amount of energy flowing both inwards and outwards, more is flowing outwards than flowing inwards. And that difference between the flowing outwards and flowing inwards radiation is what is transporting energy from the center to the surface. It's just the fact that there's more energy flowing out than flowing in, even though inside the sun there's a tremendous amount of energy flowing in both directions. There's a bit more flowing out than flowing in. And that transports energy from the core towards the surface. And that means, and this is what we mean by this radiative diffusion, it implies that it has to be hotter towards the core, because if it were everywhere the same temperature, you wouldn't have this net outward transport. There'd be just as much energy flowing in as flowing out. So it has to be that the temperature rises towards the center in order for there to be more energy flowing out than flowing in. And it has to always be true. As you get deeper and deeper down, the temperature's getting higher. That's the only way. It can always be the case that it's hotter towards the center than it is towards the surface, so that there's a net outwards flow of radiation. Make sense? What questions do you have? Yep. No problem.
So you
Yeah.
said that only stars that have like an outer convection zone
Mhm.
are ones that have spots.
Yep.
In the reading, it's showed that like larger stars, the convection zone is like closer to the core.
Correct. Yes.
So
Mhm.
would larger stars just not have stars?
Correct, yes. So high mass stars on the main sequence that are fusing hydrogen and helium don't exhibit cool star spots on them because their convection is deep in the interior rather than in the outer layers. In those stars, radiative diffusion transports the energy all the way out to the surface once you're outside the core. And so as a result, you don't get convection and you don't get spots. Mhm. At least not dark spots. They can, turns out for other reasons, have bright spots on them, but they don't get dark star spots like from magnetic fields. And in fact, those stars, their outer layers aren't magnetic either, because it turns out that the convection is an important ingredient in the generation of stellar magnetic fields. So they don't have spots, both because they don't have convection to suppress, and because the convection turns out to be an ingredient in making the magnetic fields in the first place. So yeah, that's a very good question. What's that? It can be chemical gradients. And I'm trying to think, because my name's actually on a paper that studied bright spots on a B-type star. And so now I'm drawing a blank. So I'll look that up and get back to you on that.
What is there like a name for the lack of a convection zone? I guess like it was like on the diagram, it was like the core convection zone, like photosphere.
Yeah, so this is only for lower mass stars on the main sequence, and it can also apply to high mass stars that are off the main sequence that have distended, like Betelgeuse, for example. It's probably about 10 times the mass of the sun. When it was on the main sequence, it would have been like an O or B type star and be blue and not have any convection in the outer layers. But as a red supergiant, it now has deep convection in its outer layers. And so high mass stars that have left the main sequence can in fact have spots because they have low enough surface temperatures that convection can take over in their outer layers. But on the main sequence, high mass stars do not have spots. And then your question was, is there a name for that? So well, I mean, what I would say here is this structure. I'm actually going to show another slide that gets to this point, but this structure of radiative core and radiative zone and convective outer layers flips over when you go to higher masses, where the core becomes convective and the outer layers become radiative. And there is no outer convection zone in those higher mass stars. It just doesn't exist. And that's because of the higher temperatures. So, excuse me, in low mass main sequence stars and stars that are beyond the main sequence that have become red supergiants, then you can get convection in the outer layers. Convection is rising and falling of hot and cool gas. It's the way a radiator heats a room. A radiator, a good old-fashioned radiator, warms the air near it, which causes it to expand and become less dense than its surrounding air. That makes it buoyant, so it rises up. Meanwhile, nature abhors a vacuum, if you will. So if you got air rising above the radiator, that produces a pressure gradient that pulls in air from the floor to replace it, which then gets heated by the radiator to continue the cycle. That warm air that rises above the radiator mixes in with its surroundings, transfers heat to them. So you're transferring heat from the hot radiator to the rest of the room via convection. Once that air gets to the ceiling and cools, then it can sink back down again, come along the floor, get back to the radiator again. So you set up a convection cell where the radiator is driving the convection cell. Warm air is rising above the radiator, sinking, and then coming across the floor and to come to the radiator again and continue the cycle. So you get what's called a convection cell within the room that's driven by the radiator. And that's transporting heat from the radiator to the rest of the room. In the star, what's happening is that in the convection zone, the opacity is high enough that, and the opacity is this resistance to the transport of radiation. It's high enough, and for other reasons too, it means that radiative transport is no longer efficient and convection takes over. And so in the convection zone, it's convection that's transporting energy from deeper, hotter layers to higher, cooler layers. So it's heated by the hot layers at the base of the convection zone that drives upward motion of buoyant plasma, ionized gas, towards the surface, and then it mixes in with its surroundings, transfers energy to them. Once you get to the photosphere, you're close enough to space, if you will, that the photons can just escape and fly off into interplanetary space. So you get radiation of those trapped photons. Once you get to the photosphere, the layer that produces, that radiates most of the light that we see from the sun. And then cooler gas sinks back down and continues the cycle and so forth. As we'll see, there's actually multiple layers of convection. And the photosphere is the topmost convective layer within the sun. But there are two layers below that that have larger convective cells transporting energy to the surface. So as the figure says, energy is produced in the sun's core by nuclear fusion. It's carried outwards first by radiation in the radiative zone, by that radiative diffusion process, then by convection, and then in the photosphere away from the sun by radiation, once you're essentially at the surface. Now the sun is a ball of gas, really plasma, so there's no point at which it officially ends. It doesn't have a solid surface. It just kind of fades away. But once you're at the layer that we call the photosphere, the remaining opaqueness, if you will, of the material above it is small enough that the photons can just escape at that point and fly off into space. Make sense? Okay. Does that mean, Anushka says, that supergiant stars are not likely to have star spots? In fact, no, they do tend to have spots because supergiants are stars that are post-main sequence. They are no longer fusing hydrogen into helium in their cores. So if you mean, does it mean that stars on the upper main sequence do not have spots? It does mean that, but those upper main sequence stars, once they leave the main sequence, can definitely have spots on them. Yes, indeed, understood. Yeah. Okay. And then as Phil Platt mentioned, radiative diffusion is a slow process. And so you can imagine a photon being generated by a nuclear fusion reaction in the core. It scatters off of it, turns out free electrons, because deep within the sun's interior, it's so hot that everything's completely ionized. There are no atoms because it's too hot for them to exist. And if an electron attempted to bind with the nucleus, it would immediately be kicked back off of it again. So the main source of opacity deep in a star's interior is electron scattering off of free electrons. And you can calculate the mean free path, the average distance the photon would travel before scattering off of an electron. And you can say, okay, that's the mean free path. And using an understanding of how diffusion works, it turns out, and again, in astrophysics, we'll do this in more detail, with diffusion, the amount of net outward progress you make goes like the square root of the number of steps. It's similar to the Poisson, it's a Poisson process, and so it's related to that. But you can imagine, okay, here I am in the middle of the room. I'm a photon, and I keep scattering things. And so how long till it, let's say that's the core, that's the surface, how long till I make it to the surface? Well, if I, and let's say the mean free path is 1 foot. Maybe not scale here. So if I could just go straight out to the surface, right, then I would just take however many steps are between me and the surface. But on the other hand, because of the random nature of the scattering, sometimes it scatters forward, sometimes it scatters back. You flip a coin, and if it's heads, you step forward, and if it's tails, you step back. Okay, heads. Heads, when making progress, heads, tails, and so forth. It turns out that the net distance that you have traveled is expected to be the mean free path, the average distance you travel between scatterings, times the square root of the number of steps you've taken. So if you are 100 steps from the surface, on average, it'll take you 10,000 scatterings to get there, because 100 is the square root of 10,000. 10,000 is 100 squared. The distance you get, your net distance traveled is the square root of the number of steps you take in a diffusive process like that. So you do those calculations in detail, and what we find is that a photon, although it's a little sloppy here because photons can have their energy degraded and become more than one photon, but roughly speaking, a photon generated by a nuclear fusion process in the core will take something like, excuse me, 100,000 to 1 million years to finally make it to the surface. So the light we see from the sun coming out of the sun's surface today, in some sense, was generated in the core hundreds of thousands or even 1 million years ago or thereabouts. Unlike neutrinos, the reason we like to study neutrinos is that they're generated in nuclear reactions, and neutrinos can travel through light years of matter without ever scattering from anything. When we detect neutrinos coming from the sun's core, we're seeing conditions in the core today. Whereas with the sunlight that we see, we're seeing energy that was generated hundreds of thousands of years ago. So just kind of a fun fact there. Again, not directly relevant to star spots, but still a good thing to know and to realize. So that's this business of energy from the core. It takes something like 100,000 years to reach the surface. If you think about it too, that means, so if you could imagine a photon lasting that long, and it took 100,000 years to get to the surface, then the total distance it traveled was 100,000 light years, which is the width of our galaxy, just to get from the center of the sun to its surface, which is pretty crazy to think about that. So powering the sun. The sun has been around for a long time, about 4.6 billion years. So it's got to generate a lot of energy over a long time. And the only thing that would work is fusion of hydrogen and helium in the core. So protostars, stars in formation, are not powered by nuclear fusion. They're powered by gravity, by the conversion of gravitational potential energy into thermal energy and radiation. Baby stars, protostars, are powered by gravity. That's called the Kelvin-Helmholtz process, after Kelvin and Helmholtz, famous physicists who first proposed it as the source of the sun's power. And when they proposed it, you can show that the Kelvin-Helmholtz timescale, and you will show this again in astrophysics, all this stuff that you'll get to later. Kelvin-Helmholtz contraction of the sun to power it could power the sun for around 100 million years or so. And so when they proposed this mechanism in the late 1800s, this seemed like a very plausible mechanism to power the sun, because the sun would only have to shrink a tiny fraction of a centimeter every year in order to produce its luminosity by this process. And it could last about 100 million years that way, of producing energy by this process. And at the time, they had no idea that Earth was a lot older than that, and therefore the sun was a lot older than that. But as geologists eventually showed that Earth and therefore by implication, the sun are much older than 100 million years, Kelvin-Helmholtz contraction was no longer a viable option for explaining how the sun generates its energy. It is how Jupiter generates its energy, and Jupiter radiates more than 3 times as much energy as it receives from the sun, because it is in fact slowly contracting, it's slowly shrinking and turning gravitational energy into thermal energy and radiation. And it's actually, as a result, giving off more energy than it receives from the sun. But the sun itself, that can't be the source of its energy. And in the early 20th century, when nuclear physics was worked out, that's when it was understood, aha, stars run on nuclear power. That was a huge revelation to understand that nuclear fusion is what powers the stars. And really, humanity has not known that for very long, right? It's only about a century that we've known that. Go back to that timeline video, right? In the history of humanity, even 100 years isn't very long for us to have known something. So this is still kind of new information after centuries and thousands of years of wondering what the stars were and how they shined. Only very recently did we figure that out. Is it something that we've understood? So for the sun and for all main sequence stars, we call them, remember the HR diagram, the main sequence, those turn out to be stars that are fusing hydrogen and helium in their cores. And we call it hydrogen burning, even though it's not a chemical burning. And that's what powers the sun and all other main sequence stars. Let's take another break at this point, another 10 minutes, because, right, talking and listening for long enough. So we'll resume in another 10 minutes.
100 years on the scale they may be a millimeter. This wasn't a centimeter, like wasn't.
They first made a scale for human history,
I mean, on the universe.
right? But on the universe scale, no, much less than that. Yeah, much less than that. Remember, he said that a human lifetime would be less than a human hair's width, which is less than a millimeter. Yeah. Yep.
I thought the centimeter.
On the I'd have to play it again, but I'd have to play it again because I've forgotten exactly what they said. But yeah, I mean, yeah. So this is just just going on again, just independent of that. One way to think of things is make a millimeter a century, right? Then a million years would be how long? Well, there are, again, 10,000 centuries in a million years, right? Because 10,000 times 100 is a million. So a million years would be 10,000 millimeters, right? Which would be 10 meters. So a century is a millimeter, and put that at the front of the room. A million years ago, fire being tamed is the back of the room on that scale. And the Roman Empire is 20 centuries ago, 20 millimeters, right? That's 2 centimeters away, right? Now our ancestors who were not Homo sapiens yet, Homo erectus, I think it was, tames fire a million years ago. And we think of, the Roman Empire's ancient history so long ago, it's 2 centimeters away, right? Compared to that. Agriculture, 10,000 years ago. So that's going to be 10,000 years is 100 centuries, right? And so that's going to be 100 millimeters, 10 centimeters away, right? Homo sapiens has existed for about 200,000 years, and agriculture, for 190,000 years, we didn't have agriculture. 10,000 years ago is when agriculture develops. So most of human history was pre-agricultural, and it's just so fantastically fast that we have developed technology, right? In other words, the scientific revolution was about 400 years ago. So 4 millimeters away, right? That's all that 4 millimeters. that's part of the problem with things like climate change and so forth is we don't have a perspective, right? In other words, when we talk about how fantastically rapidly we're changing the climate and that we're in the middle of a mass extinction right now that humans are driving, people say, I don't see species going exist all around me. I don't see the climate getting, I don't think it's like a lot warmer than it was when I was born. What are y'all talking about? No, you're not understanding what tiny fraction of a period we're living in compared to geological timescales. I mean, we're practically overnight changing the climate and causing extinctions. We're in a ferocious extinction event right now. And people don't understand it because they don't have a perspective of how short our lives are compared to, people think 100 years is a long time. It's not a long time. It's such a tiny amount of time, et cetera, et cetera, et cetera. Okay, now we'll start taking the break. And I'll start. And I'll pause the recording.
That's something that was definitely not like really down upon in like history classes, is like how recent things are.
Yeah, right.
Possible.
Yeah, you got to be nice to it. You might have that looked at just to be sure,
I
Yeah,
was gonna schedule an appointment when I have a lot to do when I go back home. I
yeah.
have to get my license renewed since I'm turning 21.
Right. You go from vertical to horizontal.
Finally.
Yes.
Then I gotta get my hair cut, 'cause I've been putting it off, like every semester I'll get my hair cut before the semester. And then maybe on break.
Yeah,
And then see where it goes.
yeah. My lovely wife likes my hair shorter, but I tend to get to the point because I'm just so busy, where she's like, you need a haircut, you need a haircut, you need a haircut.
That's how my dad is.
Yeah. But right now I got it pretty short and I actually got another haircut right before going on the trip. So I'm just like, yeah.
My hair, the last time I got my hair cut, it's gotten really long.
Yeah.
So,
There's an easy fix for that.
yeah. The last time I tried to cut my own hair though, I ended up looking like, I don't know if you've ever seen Shrek, but Lord
Oh, yeah.
Farquaad.
Oh, yeah.
I tried to give myself 2 little like front pieces and I ended up doing the like berries and cream boy. from
Okay.
That commercial.
I'm going to blow your mind. There are people you can pay to cut your hair and they're professionals.
But the key
And
word to that sentence is
hey, I see. There are some things worth paying for.
Oh, I'm great.
I mean, just go to a place like Great Clips or something like that. You don't have to go to some fancy schmancy,
Because my mom's close
Aveda.
friends, so she
Ah.
does offer, like, discount rates,
Ah.
but the discounted rate is still.
So my cousin, she's a hairdresser. She just does like, she pays or she charges for haircuts. Like if you're family, she's just like, oh, free. But
Oh,
it's like
nice.
more than just like a simple. That like this,
Yeah,
I just go in just a little bit. I can see that.
yeah.
My cousin's a cosmetologist, but she lives in Georgia, so I just
Ah.
like trip.
Right. Yeah, during the pandemic, I was having my wife cut my hair because I didn't want to go to a barber and get COVID that way or whatever. And you watch these videos, right? There's all these how you can cut your own hair or how you can cut somebody else's, and you watch the video and it looks very straightforward. Yeah, I can do that. And then you try it yourself and it's like, I can't do this, And so I says, she was not very fond of having to cut my hair, But it was serviceable, I was like, come on, just calm down. It just needs to be good enough for Zoom, And I actually was like, no, I don't think I guess I did. I think I was gonna cut her hair, but she wouldn't let me. Yeah, which is probably smart, but I did try to cut my own hair some. And yeah, less than ideal, but good enough for Zoom.
During the pandemic, I went a little stir crazy and I tried to cut my own hair and I ended up doing, I don't know how, but it turned out like that.
Oh, yeah,
And I started freaking out and my mom ended up fixing it for me.
yeah,
And yeah, I was like, I'm so bored. I'm so bored, chop.
yeah, yeah. Yeah, my,
True.
that's
It
one
wasn't this
approach, yeah, right, but yeah. Yeah, I know some people that just like, yeah, there's just their COVID locks, basically.
Yeah.
Yep. Yeah. All right, back to our story, shall we? Yeah, so nuclear fusion does not cause star spots. But on the other hand, you wouldn't have star spots if there wasn't nuclear fusion, right? Because you have to have the powering the star and all that kind of stuff. So again, we'll go into much more detail in astrophysics, but basic idea is that nuclei contain protons. The simplest nucleus is hydrogen, which is typically just a proton. So because protons are positively charged, nuclei electrically repel one another. And that means that at low temperatures, nuclei will not fuse because they're not moving fast enough. They'll just veer off course or go backwards before they ever come close enough to feel the effects of the strong nuclear force, which over short ranges is a more powerful attraction between nucleons than the electromagnetic force is a repulsion between them. And so at high enough temperatures and therefore fast enough motion of the particles, they can get close enough for the nuclei can get close enough for the strong nuclear force to make its effects known and bind the nuclei together and thus produce fusion. Now, this isn't stated here, but in fact, quantum tunneling is crucial in the fusion process because if you calculate how close the protons would come to one another classically at the temperature of the sun's core, the answer is that they would veer off course and move away from one another before the strong nuclear force could produce any significant binding. However, because of quantum mechanics, there's a small but non-zero probability that they would, in a sense, find themselves much closer than would be predicted classically. And in fact, when you run the numbers, you find that tunneling is absolutely crucial to the fusion process in the sun. It allows it to take place at much lower temperatures than you would predict from classical physics. So the first stage in the so-called proton-proton chain that powers the sun is proton plus proton produce a deuteron, a hydrogen nucleus where one of the protons has turned into, well, where a hydrogen nucleus where it's a proton and a neutron instead of a single proton in the nucleus. So what must have happened is one of the protons turns into a neutron. How does it do so? It does so by emitting a positron and a neutrino. And the positron is an antimatter electron. So it will very quickly find a regular old electron and they'll annihilate with one another and turn into a pair of gamma rays. And then the neutrino just streams out of the sun and off into space because neutrinos are very standoffish and don't interact with anything. So we do get a flux of neutrinos from the sun's core that we can detect with specialized detectors. And again, that's the bit of we see conditions in the sun's core today when we detect the neutrinos. So that's the first step. Any given proton in the sun's core, on average, it's about 7 billion years before it undergoes a fusion process like that. How old is the sun? Do you remember? Drop another billion off of that. Yeah, about 4.56 billion years old. The average time for a proton to fuse with another proton to form a deuteron is 7 billion years. That means every proton that has ever fused in the sun has beaten the average so far. The average is 7 billion years, but some of them are going to do it tomorrow. Some of them are going to do it in 3 seconds. Some of them are going to do it in 7 billion years, right? Or, well, not anymore because the sun will have left the main sequence by then. But in any case, every proton that's ever fused in the sun has beaten the average. Congratulations to all of them. The full process, do I have it here? Yeah, here's the full process. I'll go backwards. So the full process is the first step is proton plus proton makes a deuteron, a proton plus a neutron like that nucleus. And then in the next step, which only takes a couple of, it's like very quick, like, minutes or less. Because, excuse me, deuterium has a very high reaction cross-section. It loves fusing. Very quickly, another proton fuses with the deuterium to form a helium-3 nucleus, 2 protons and 1 neutron, a light isotope of helium. And then on average, 400,000 years later, the helium-3 nucleus finds another helium-3 nucleus that was made the same way to produce a helium-4 nucleus, but there's 2 extra protons left over, so they just fly out of the reactor and they can participate in fusion again. So the net reaction is that, well, we start with 1, 2, 3, 4, 5, 6 protons go in, but 2 of them fly out instead of forming part of the final helium nucleus. So the net reaction is 4 protons become a helium nucleus by having 2 of them turn into neutrons. And so that means that you're going to spit out 2 positrons and 2 neutrinos, but the positrons are going to annihilate with electrons to form gamma rays. And gamma rays are formed in the fusion of a proton with deuterium to form helium-3. And so the net reaction then is 4 protons make a helium nucleus, 2 neutrinos, 2 positrons, and 2 gamma rays, but those positrons annihilate with electrons to quickly form 4 more gamma rays. So really 6 gamma rays come out of it. And so that's the most common procedure by which nuclear fusion proceeds in the sun. There are some side chains and another process called the CNO cycle that also produce fusion. But the point is that the mass of a hydrogen 4 nuclei, of 4 hydrogen nuclei, I should say, is 1.007 times larger than the helium-4 nucleus. Relativity says E equals mc squared. There's a certain equivalence between mass and energy. So that difference in mass, 0.7% difference in mass, is released as energy, and that's what's powering the sun. Now, it's not true, by the way, as an aside, that the sun's mass decreases every time you form a helium nucleus, because in relativity, energy, again, is equivalent to mass. So while those photons that were produced are still inside the sun, they contribute to the sun's mass because of their energy. The sun loses mass only because of its luminosity, because of the photons that are leaving the surface. So it's luminosity that is causing its loss of mass via nuclear fusion. It's the photons leaving the surface that are responsible for the lost mass associated with nuclear fusion. It's not the nuclear fusion itself. As long as the energy is still inside the sun, it's contributing to its mass. As an aside, fusion takes place in the core where it's hot enough. The main fusion process is the proton-proton chain. There's actually a couple of side branches. The one that we showed is called PP1. There's also proton-proton PP2 and PP3, which are other reactions that occur a bit less frequently than PP1 does. PP1 is about 69% of the time. But there's also the CNO cycle, which involves carbon, nitrogen, and oxygen acting as catalysts that still has a net reaction of 4 hydrogens produce a helium plus energy. So just fun fact about how the sun is powered. I've memorized the proton-proton 1 chain, the PP1 chain that was on the prior one there. I'm not going to memorize the CNO cycle because it's too freaking complicated. I just look it up if I need to. But why not say what happens just for kicks here? Why a carbon-12 nucleus, 6 protons, 6 neutrons, fuses with a proton to form a nitrogen-13 nucleus. So nitrogen-13 is going to have how many protons and how many neutrons? What's nitrogen on the periodic? What's carbon on the periodic table? It's element number 6. So it's got 6 protons. So carbon 12, 12 is the atomic mass, it's the number of protons plus neutrons. So carbon 12, 6 protons, 6 neutrons. You add a hydrogen to it. How many protons do you have? 7. 7 makes it nitrogen. Nitrogen's element number 7. It's nitrogen 13 because there's 6 neutrons, so 13 total subatomic nucleons, protons, neutrons in the nucleus. That isotope is less common than nitrogen 14, 7 protons, 7 neutrons. But the nitrogen, so a gamma ray is released also in this fusion because nitrogen 13 has a bit less mass than carbon 12 and hydrogen and a proton put together. So the difference is released as a gamma ray, carries off that extra energy from the loss of mass, if you will. But nitrogen 13 is an unstable nucleus, and so it quickly decays into carbon 13 by emitting a positron and a neutrino. So what has happened? What turned into what within the nitrogen 13 to produce the carbon 13? Did a proton become a neutron, or did a neutron become a proton? So carbon 13 has how many protons? 6. And nitrogen 13 has how many protons? 6. So did a proton become a neutron, or a neutron become a proton? A proton became a neutron, right? So you go from nitrogen 13, 7 protons, 6 neutrons, to carbon 13, flip that around, 7 neutrons, 6 protons. And again, that takes place by what's called a beta decay, because beta particles are electrons or positrons. So it's a beta plus decay. It emits a positron, which will quickly annihilate with an electron, and an electron type neutrino. And then the carbon 13 fuses with a proton, a 1H, a proton. And now we bump up to one more nuclear particle. So we go from 13 to 14, and it's a proton that we've added to those 6 neutrons. So we get nitrogen 14. Nitrogen 14 is a stable nucleus, so it doesn't undergo a beta decay, but a proton can come and fuse with it to make oxygen 15, 8 protons, 7 neutrons, which is unstable. It undergoes a beta plus decay. A proton turns into a neutron to produce nitrogen 15. And then a proton fuses with the nitrogen 15, but that splits it into a carbon 12 nucleus and a helium 4 nucleus. So notice that 1, 2, 4, can't count. 1, 2, 3, 4 protons fused ultimately to make a helium 4 nucleus, and we've recycled the carbon 12. What do you call, so in chemistry, there are some reactions where you have a compound, a molecule that doesn't get used up in the reaction. Similarly here, carbon 12 isn't getting used up because it's recycled at the end again. I've said the word already. What do you call a reactant that is also a product, so it doesn't end up getting used up? It keeps getting recycled and able to repeat the cycle again. It's a C word. It's a catalyst. It's a catalyst. Yeah. In chemistry, a chemical catalyst is a chemical that is not only a reactant, but it's also a product, so it keeps getting recycled. So carbon 12, we say here, is a nuclear catalyst. It doesn't get used up in this reaction. The sun makes something like 10% of its energy via the CNO cycle. But as you go to more massive stars, you get more and more of the energy produced by the CNO cycle, and that will have relevance. We'll see that that's the reason why massive stars have convective cores, whereas lower mass stars have radiative cores. The CNO cycle is extremely temperature dependent, and it turns out that makes the core be convective rather than radiative. But anyway, let's start talking about spots. So I've already mentioned that spots are cooler and darker than the surrounding photosphere, and that they're not really completely black like photographs might make it appear to be the case. It's just that they're emitting less light than the rest of the photosphere is, and so they're dark in contrast with the rest of the photosphere. And they're big. You know, you look at a photograph of the sun and the sunspots don't look that large, but that's because sun big, right, is the technical terminology there. Sun's more than 100 times bigger in diameter than the Earth. And so something that looks small compared to the sun could still be quite large compared to the Earth. And a large sunspot group is an example of that. Here's a photograph of an actual sunspot group and the size of Earth for comparison. They grabbed the Earth and moved it close to the sun in order to take this photograph one day in order to make this comparison. Or maybe they used Photoshop, or maybe they just drew a dark circle or something like that. But this is the actual size of the Earth compared to that sunspot group there. There are stars that have spots that are much larger in comparison to the stars than spots are compared to the sun. And there are stars that are subgiants, which is the case for the poetically named HD 12545 here. A subgiant is a star that is off the main sequence, fusing hydrogen in a shell surrounding the core rather than in the core itself, as you read about, on its way to becoming a red giant. So this star is a subgiant on its way to becoming a red giant. So it's considerably larger than the sun, but not as big as a full-on red giant is, as big as it's eventually going to get. And that star has a very strong magnetic field in its outer layers and produces spots that, one, are much larger compared to the star than sunspots are compared to the sun. Sunspots never occupy more than about 2% of the sun's total surface area, and that's when the sun is very active. Whereas you can see this spot here on HD 12545 imaged via a different technique that we're using called Doppler imaging, which works better than photometric imaging because you've got more detail. You've got more information in a spectrograph, which is what is used. The star spectrum, distortions in a star spectral line due to spots are used to map the spots with Doppler imaging. But it's harder to do. A smaller number of stars can be Doppler imaged. And so photometric imaging, like I do, can be used on a wider variety of stars, which is why it's still worth doing, even though it doesn't work as well as Doppler imaging does. But this star could be Doppler imaged. And so there's the star spot imaged by Doppler imaging. And as you can see, not only is it bigger compared to the star than sunspots are compared to the sun, it's bigger than the sun because that star is, huge. And so that spot could swallow the sun. And so this is a star where you would be able to see a very noticeable signal as it rotates of it become dimmer when the spots are more visible to us. What questions do you have at this point?
So again, in the readings,
Mm-hmm.
I know it talked about like some star spots come in like pairs.
Mm-hmm.
Kind of like goes out.
Yep. Mm-hmm.
Do they always come in pairs or are they?
So first of all, notice that the upper right there's another smudge, right? So this actually, I'm pretty sure this model, if you rotated it, we're just seeing one aspect, there's another big spot there. So they are like a pair on this. But the sun does sometimes exhibit so-called unipolar spots. And in that case, it's not that the magnetic field structure is so different than you get when you have a pair of spots. It's just that often, jumping ahead here, we talk about leader spots and follower spots in the direction of the sun's rotation. Turns out that the magnetic field lines tend to be more concentrated in leader spots than in follower spots. And what can happen is that the magnetic field is strong and concentrated enough on the leader side, the side that's ahead in the direction of the sun's rotation, than on the follower side, such that you only get one spot because the magnetic field on the other side isn't concentrated enough to produce another spot, even though it's there. So you always get both senses of magnetic polarity. You get arches that go connect different parts of the surface to one another, but you don't always have a spot at the foot points of at both foot points of the magnetic arches is what it comes down to.
How common is that?
It's pretty common, actually. It's not at all uncommon to see single spots on the sun. In a complex, in a very large sunspot group, it's always going to be bipolar spots like that. But if you have a relative, if you have a single, you can have a single spot that can be bigger than the Earth and not have a companion spot of opposite polarity. But in a magnetogram, which we'll get to, you'll still see opposite polarity flux there. It's just that it's not concentrated enough to suppress convection enough to form another spot.
What about like with HD 2545?
Mhm.
Would that be more rare?
So we do often see what look like unipolar spots when we make these star spot maps like this. But on the other hand, they're not high enough resolution to what looks like a big blobby spot here could really be a spot group on the actual surface of the star. So we can't tell for sure is what it comes down to necessarily. Yeah. But it's reasonable to assume that you often would have pairs of spots on other stars that are connected by arches and so on and so forth. What other questions do you have? Okay. So this is an illustration of this idea of the photosphere, because we'll be talking a lot about stellar photospheres because spots are surrounded by the photosphere of the star. Photosphere literally means sphere of light. When we look at the sun, it looks like it has a solid surface, right? If you take a picture of the sun, it looks like a solid ball. And early astronomers thought that it was solid as a result of that. It is not. It's a ball of gas, or more strictly speaking, it's a ball of plasma, of ionized gas, because it's so hot. Although don't imagine that the surface layers are completely ionized. It turns out that most of the atoms in the sun's surface layers are not ionized because it takes a temperature of around 10,000 Kelvin to ionize hydrogen under stellar conditions, and the sun's surface temperature is about 5,800 Kelvin. So the hydrogen is primarily unionized. It's neutral. But metals, which again mean anything that's not hydrogen or helium, because they have inner electrons shielding partly the positive charge of the nucleus from the outer shell electrons, they tend not to hold on to their outer shell electrons very tightly. So metals tend to be relatively easily ionized. And so metals are the primary source of the free electrons in the sun's outer layers and responsible for the fact that it's a plasma, an ionized gas. But it's only a partially ionized gas in a star that it's at solar surface temperatures. It's not hot enough to be fully ionized. In hotter stars, like OB type main sequence stars, then it's hot enough that their outer layers are completely ionized. It's ionized hydrogen rather than mostly neutral hydrogen. Again, metals are relatively easily ionized under solar atmospheric conditions. It turns out, and sometimes this is surprising to students the first time they hear this, it turns out that a hydrogen atom can actually bind two electrons. It can actually have two electrons orbiting the proton. That's called the H- ion. And if there weren't any metals around, you wouldn't make H- because if you have, where would the electron to make an H- come from? If the sun was pure hydrogen, it would have had to have come from another hydrogen atom. But that electron can bind much more strongly to a proton, a bare proton, than it could to a neutral hydrogen. And so the reason why the sun has H- in its atmosphere, in its outer layers, is because metals easily lose electrons. So now you've got all these spare electrons around that can bind to neutral hydrogen atoms to make the H- ion. But that second electron is very loosely bound. There's only one bound state, and its binding energy is a fraction of electron volt, such that any visible light photon has enough energy to strip that extra electron off of an H- atom. And that means that H minus, it turns out, is the primary source of opacity at visible wavelengths in the sun's outer layers. And it's the reason why the sun appears to have a solid surface. It means that the opacity, the ability to absorb light is high enough that we can only see about 400 kilometers into the sun or so, once you reach this layer called the photosphere. And so what it means, is kind of illustrated by the figure here, is that most of the light that we see comes from a layer about 400 kilometers thick in the outer portion of the sun. That's the photosphere, because photons starting out deeper than that are going to get absorbed or scattered before they fly out into space. Only photons that start within about 400 kilometers of the top of the photosphere are able to fly out into space without scattering again before getting there. And that means the light appears to us to be coming from this layer about 400 kilometers thick. Now, if you could get close enough to the sun to see that, you would see that it looks fuzzy. You know, in other words, you could see about 400 kilometers into it. Well, assuming you weren't blinded by the light, which you would be, the sun's surface would look fuzzy because it's 400 kilometers thick. That's much further than you can see in Earth's atmosphere, for example. But 400 kilometers is a very tiny fraction of the sun's diameter of about 1.3 million kilometers. In other words, if I do this, I'm going to draw the sun. Here's the sun. There's the sun. That chalk line is way thicker compared to my circle that I drew than the photosphere is compared to the actual sun. Even if you drew it with a fine point pencil, and you drew it like, as big as this room, that pencil line would be too thick to represent the photosphere compared to the sun. So because we're getting the light from such a thin layer compared to the size of the sun, it gives us the illusion that the sun is solid, that it has a sharply defined surface. But it's just an illusion because that layer is thin compared to the size of the sun. And that layer is what we call the photosphere, because most of the photons that we see last scattered in the photosphere before flying off into space. So when you see a photograph of the sun, or you look at it with the telescope, or project it during the eclipse or whatever, right, before it's totally covered, that's what you're seeing as the photosphere. And the spots are embedded within the photosphere, is what it comes down to. What questions do you have? Should I push the magic button? All right. So here is here's the Swedish Solar Telescope, except I can't resist the urge to say, here's the Swedish Solar Telescope. I just can't stop myself from doing that. Sorry, I have to. Notice it's very different looking from typical telescopes because the sun is freaking bright. You don't need a big mirror in order to gather enough light to see the sun. In fact, you don't want a big mirror to observe the sun. You'll fry everything if you do that. So it's got a very different design, and it's got this folded optics in this tube that goes down, and then the light is beamed down that shaft through that support structure. And the Swedish Solar Telescope uses adaptive optics in order to de-blur the image. In other words, turbulence in the atmosphere is what makes stars twinkle, and it also limits the amount of detail that we can see in images because it looks like you're looking through, like if you look at the road on a hot day and you see the shimmering, you look at stars, you look at planets, you look at the sun, you see this shimmering everywhere that's blurring because of atmospheric turbulence. But you can use computers and have movable mirror elements and so forth, where you can rapidly deform the shape of the mirror to compensate for the deformation of the wavefronts due to the atmospheric turbulence. It's an amazing bit of engineering, and you can sharpen the images as a result. Now, the Swedish Solar Telescope, when it was built, was making the sharpest images of the sun ever made. It's now been surpassed by an American telescope, USA. But nevertheless, I'll show you these lovely images from the Swedish Solar Telescope. So here's one that in magnificent detail shows the structure of a spot group. So the central part here, the darkest part, is called the umbra, which is from the Latin word for shadow. And the filamentary looking outer part of the spot is called the penumbra. And you may know from the eclipse and all that, that the darkest part of Earth's shadow is called the umbra and the lighter part is called the penumbra. So we use the same name for those parts of the spots because when people first started studying, they thought they might be shadows of stuff on the sun. And so it's funny terminology, but it has stuck. And so large spots tend to have both an umbra and a penumbra. Smaller spots called pores often only have umbra. They don't have penumbra surrounding. You'll just see like a little black spot. And then meanwhile, notice this pattern surrounding the spot. This is the photosphere, and these are what are called the granulation, granules, which again, that would have been in the reading too, but it doesn't hurt to repeat everything. Repetition is the key to learning. So these are granules because they look kind of like little grains of sand or whatever, or grains of rice or whatever. And the entire photosphere outside spots is covered with this granulation. Again, the technical terminology for the sun is sunburn. And so we have to keep in mind that maybe these things are bigger than they look, and they are. Each one is roughly the size of like Texas and Oklahoma put together. About 1,500 kilometers is the typical size for one of these things. And each one only lasts for about 10 or 15 minutes or so, because what these are the tops of convection cells in the photosphere. The photosphere is the topmost convective layer within the sun. Here is a photograph from the Swedish Solar Telescope near the limb of the sun, LIMB. The limb refers to the edge of the disk. So that's just standard astronomical terminology. If you look at the sun or the moon or a planet, the edge of the visible disk is called the limb. So here's a photograph from the Swedish Solar Telescope near the limb, and notice that the granules look puffy. They look like the centers of them are higher up than the edges, and that's not an illusion. They really are. They are puffy because the centers of the granules is where warmer gas is rising, and the boundaries between the granules is where cooler gas is sinking in this convective flow. So here's a cartoon from the book that I use in Astronomy 111 that illustrates the idea. So on the right is an actual photograph of solar granulation. And so here you can see, here's one granule. The center is brighter than the edges because it's about 100 Kelvin warmer in the centers of granules than in the edges. So the sun's average surface temperature is like 5,800, but the centers of the granules are like 50 Kelvin above that, and the edges are like 50 Kelvin or so below that, because warmer gas is rising at the centers and then sinking along the edges in the intergranular lanes, they call it. That's a good word. So here's, imagine taking a cross section and getting into the, looking from the side, warmer plasma flowing up towards the center, sinking down along the edges. So think of it as like a rolling donut, if you will. In other words, think of a torus and think of a donut where it's like spinning, rising up in the middle and sinking along the edges in 3 dimensions here. So here is a video, a time-lapse video where you can actually see this in action, which is pretty cool. Sun may seem still, it's always bubbling because it's not showing the whole thing. Oh, that's it. When I wanted to play it, does go. So DKIST is the American telescope, but it's active now, exceeds the Swedish solar telescope, that Daniel K. Inouye solar telescope. So, actually, let me see. So I thought there's another. Okay, we'll get to that. I want to see. I thought I had this other video that shows the convection tour. How this. Here's everything you're gonna. Okay, no, I'm just. I take that. Because there's this video that shows how you can simulate the solar granulation in a way that I simply wouldn't. It's like, oh, it's just simple. You just get the silicone oil and heat it up to like some really high temperature with these particles in it. I'm like, you're crazy. I'm not going to do that. I'm going to hurt myself. But let me see if I can just find it on YouTube because I do like the video. So. Solar granulation simulation. Maybe that. Oh, here's a nice one too. Anyway, just check that out, right? So this is actual solar granulation. So you can see that each individual cell disappears, but then it's just replaced by another one. What's that? Oh, it's not. Oh, that's right. I forgot that I'm not. Yeah. Okay. Wasn't that amazing? Oh, it's just incredible. Stop it. Stop it. Stop it. Stop it. There you go. Yeah, I guess I should let you see it too. Ooh. That's what gets suppressed inside sunspots. And there's the video we just saw. There's a little bit of Carmen. Some fire. Spend so long looking for this. Let me just find it. In fact, maybe I'll find it while we're taking our break right now. Since it's about time. Resume recording. Anyway, here is the video I was talking about, where I would not particularly do this experiment because I'd be afraid I'd hurt myself, but still it's a good experiment.
Energy is produced in the core of the sun through nuclear reactions. Small nuclei combine to form larger nuclei in nuclear fusion and release energy in the process. That energy then makes its way toward the surface of the sun. There are three major modes of thermal transport: conduction, convection, and radiation. This is our second video looking at thermal transport in the sun, and will specifically study convection, which is the dominant mechanism in the outer part of the sun. Convection is the actual movement of material in fluids due to buoyancy. Hotter material has relatively lower density, and thus it rises, much like a hot air balloon. Cooler material has higher density, and thus it sinks. We can easily illustrate convection with the following equipment: hot plate, small pan, silicone oil, and aluminum powder. We simply place our silicone oil and aluminum powder mixture into the frying pan and heat. It is possible to ignite the oil, so one wants to know the safe temperature range for the specific type of oil that they are using. Very high temperatures are not needed in this demonstration, and I have set the thermostat for 350 degrees Fahrenheit. As the oil heats up, convection cells are created. Hot material, initially in contact with the bottom of the pan, moves upward and boils over. Cooler material then circulates downward. The aluminum powder serves as a tool that allows us to see the circulation.
Whoa.
Here you can see two screens with a visible image on the left and an infrared image on the right of the convection cells in the silicone oil. Realize that in the infrared image, temperature is indicated by color. The white and bright yellow regions are hotter, while the dark and lavender regions are cooler. So material we saw moving upward in the visible video is shown to be hotter in the infrared image, while material circulating downward is cooler. Convection like this on the surface of the sun is known as granulation. The material that is moving upward at several kilometers per second toward the surface appears brighter, and the cooler material moving downward is darker, giving the sun this mottled appearance. Convection cells on the sun are about 1,000 kilometers in diameter. Let's look at a fun example of convection commonly used today in physics classes, known as a teabag rocket. We basically steal the paper cylinder that encloses the tea and use it to display convection. We are going to light the top of the paper cylinder on fire. Let's see if we can predict what will happen. Classroom students should follow normal procedures or instructor guidelines. Viewers not in a classroom should record.
Okay, what's going to happen? What will happen to the burning paper cylinder due to convection? It will A, implode, B, explode, C, gently rise, D, burn to ashes, E, take off like a rocket. What do you think it's going to do? What do you think it's going to do?
Things it's called a rocket. So
Okay, so you're going with it. So everybody says E?
Without the context of the rocket, I probably would have said C.
yeah, me too.
Okay, let's see what happens.
Your vote and explain your reasoning on a piece of paper. Please pause this video and answer the question.
Stop.
We light the top of the paper cylinder on fire and wait for convection to lift it up into the air. The flames heat the air trapped inside the cylinder and above it, lowering its density. Cooler, higher density air from outside the cylinder rushes in to fill the void under the flames, and a convection current is started. As soon as enough of the tea bag is burnt away to lower its weight, our rocket is born.
And yet,
More teaching materials can be found on the web at astro.unm.edu.
I know, they fooled you, didn't they?
It went pretty fast.
It
for a
did,
teabag.
it did. I mean, I might give it to you, you know. Okay, up, now it's hidden in the
This
back.
video is the third in a series of videos exploring thermal transport and focuses specifically on conduction. Thermal transport mechanisms include radiation, convection, and conduction. Conduction involves
Yeah.
particle-to-particle contact. It involves
Okay, there we go. Anyway. And now I have to get the other one back. Let's see, that could be fun. There we go. Hooray, it's back again. And there was much rejoicing. All right. So how do we know that sunspots are magnetic phenomena? Well, that was first discovered by the astronomer George Ellery Hale. I believe that was in the 1930s, and he made use of what's called the Zeeman effect. I don't know if you folks talked about the Zeeman effect in 280. It might have showed up there, but it might not have. So you would probably remember the word Zeeman if you had seen it. The idea is that there are, remember that there's, energy levels in an atom. And in hydrogen, for example, and in other elements as well, all the orbitals with the same value of the quantum number L, and also the same value of N, the principal quantum number, have the same energy. They're what we call degenerate. Their energy doesn't depend on the L value. Sorry, it doesn't depend on the M value, the value of the quantum number, which tells you the Z component of the angular momentum. So see if you remember, like for hydrogen, well, I don't know what we can't articulate today. So in chemistry, in like high school chemistry or college chemistry, you would have heard of this stuff too. So remember that there's a principal quantum number, n equals 1, 2, 3, 4 for hydrogen, which, and for the spectroscopy for that matter. So, that determines, in hydrogen, it's what determines, for the most part, the energy of the electron. Then, and it's related to the, in terms of quantum mechanics, it's related to the radial part of the wave function. The angular parts of the wave function are related to the angular momentum of the electron, and those are specified, described by quantum numbers L and M. Did you talk about spherical harmonics at all? Doesn't matter if you did. You'll certainly talk about them in 380 if you didn't talk about them in 280. And in a chemistry class, L, that quantum number, you would have called the orbitals like S, P, D, F, things like that. Like, do you remember like 3s, 3p, 3d orbitals and stuff like that? Did you take chemistry and see those sorts of things? Okay. So that's actually referring to the overall orbital angular momentum of the electron. It's out. And the rules for the quantum numbers for N and L are, do you remember? L goes from what value to what value in steps of 1. You may not know this.
Is it like 0 to N-1?
Yes, 0 to N-1 steps of 1. So if the principal quantum number is 3, L can be 0, 1, or 2, for example. And L equals 0, meaning there's no orbital angular momentum, is what we call an S state in other notation. L equals 1, which means that the orbital angular momentum actually is L times L plus 1. So it's actually the orbital angular momentum in magnitude is, it turns out, the square root of L times L plus 1 times h bar. So if L is equal to 1, the orbital angular momentum in magnitude is the square root of 1 times 1 plus 1, or 1 times 2 times h bar. So it's the square root of 2 times h bar. This is not going to be important anywhere beyond this. I'm just talking about it and seeing if it jogs some memory. Anyway, L equals 1 is what in other notation is called a p state, little p state. And L equals 2 is what is called a d state. So if n is equal to 3, L can be 0, 1, or 2, or in kind of chemistry speak and also physics speak, we have 3s, 3p, and 3d orbitals available to the electron, but not 3f, because f would correspond to L equals 3, and that's not available when n equals 3, because it goes from 0 to n minus 1. And then there's another quantum number m, also called m sub L, which is the z component, which specifies the z component of the orbital angular momentum. And so the z component is m sub L times h bar. And m sub L, do you remember what values it can go between? Minus L to L in steps of 1. So if L is equal to 1, m sub L can be 0, can be minus 1, 0, or 1, because that's minus 1 to 1 in steps of 1. That makes sense? Okay. So if L equals 2, what are the possible values of m sub L? Negative 2 to 2 in steps of 1. So if we make a list, minus 2, comma, but it's in steps of 1. Minus 2, minus 1, 0, 1, 2. Yep. So that's illustrated in the figure there. We've got 2 states which have values of L equals 1 and L equals 2. And if the electron, if L equals 2 is the high energy state and L equals 1 is the lower energy state, it could be for 2 different values of n, for example. It doesn't have to be the same n value. If L equals 2 is the higher energy state, L equals 1 is the lower energy state, then when there's no magnetic field, all the different m sub L values for a given L have the same energy. So in other words, it doesn't matter what m sub L is. The energy of the transition is given by h nu naught, where that's whatever the energy difference is between the upper state and the lower state. But in the presence of a magnetic field, we break the degeneracy so that, and that's because the electron's orbital angular momentum interacts with the magnetic field and contributes to the energy of the electron, such that the different m sub L values have different energies in this case, instead of all the same energy. So in this energy level diagram, what was a single energy level splits into 3 energy levels, with ML equals 1 having a higher energy than ML equals 0, having a higher energy than ML equals minus 1. There's small energy shifts induced by the presence of the magnetic field. And similarly, for L equals 2, you get 5 closely spaced energy levels, whereas before there was a single energy level, because before, without the magnetic field, m sub L doesn't matter. The energy doesn't depend on the z component of the angular momentum, because there's no special direction in space in the absence of the magnetic field. But if there's a magnetic field, the magnetic field defines a special direction in space, which we can call the z-axis, and then the energy can depend on the value of the z component of the angular momentum. That's what is happening here. So what had been a single energy level splits into 5 separate energy levels, 1 for each value of m sub L. So now, instead of a single transition, a single energy of photon being possible, going from L equals 2 to L equals 1. Now there's multiple energies possible because it matters what the ML is for the initial state and the final state. So the energy level diagram becomes more complicated. You're looking puzzled, Julia. What is your puzzle? Yeah, okay, yeah, I know, it's all right, okay. And again, we're not gonna be using this beyond here, but I want you to understand the basic principle of what's going on here. Now, there are what are called transition rules, and again, I don't know if you saw those in 280 or not, where there are rules on what the changes in the quantum number can be for a transition of the electron between two states having different energies. And so does that sound familiar at all? So for what's called a dipole transition, which is the highest probability type of electron transition, the selection rule is that the change in the ML quantum number has to be plus or minus 1 or 0. And so that means, for example, that an electron that starts out with M sub L equals 2 cannot jump down to M sub L equals minus 1, because that would be a change of 2 minus minus 1, or delta M sub L would be 3 in that case. And that's not allowed because delta ML can only be plus minus 1 or 0. So in other words, while in principle you can imagine drawing an arrow between any line on the top and any line on the bottom and figuring out what energy that is, which would be proportional to the length of the arrow in an energy level diagram like this. In reality, you can only draw arrows between levels that satisfy delta ML equals plus 1, minus 1, or 0. And so that means that we actually can only have 9 possible transitions that are illustrated here. Here's all the ones which have delta ML equals 0, for example. In other words, it starts at an ML equals minus 1 level and ends at an ML equals minus 1 level. And similarly, it could start at ML equals 1 and end at ML equals 1, start at ML equals 0, end at ML equals 0. Meanwhile, you could also have delta ML equals plus 1. So in other words, here it's starting at ML equals 0, ending at ML equals 1, and so on and so forth. And if you look carefully here, you find that even though there's 9 transitions here, there's only 3 different energies because there's really only 3 different lengths of arrows here. So in the end, without a magnetic field, electrons jumping between those energy levels, the original 2 energy levels, where it doesn't matter what M sub L is, would produce a single spectral line. But with the magnetic field breaking the degeneracy, it splits into 3 spectral lines corresponding to the 3 different possible energies of transition there. Again, there's 9 transitions, but only 3 different energies, because there are groups of 3 transitions that all have exactly the same. There are 3 groups of 3 transitions that all have the same energy. So this is the kind of thing, it sounds complicated. You have to kind of wrestle with it and sit with it and look at it carefully, but that's what it comes down to. In this particular case, without a magnetic field, a single spectral line. With a magnetic field, 3 spectral lines with slightly different energies. And notice that the shifts in the energies compared to the H nu naught, the energy without a magnetic field, they're proportional to B. They're proportional to the strength of the magnetic field. And this gives us a way to measure the strength of the magnetic field on the sun, because we can look for the Zeeman effect. And the stronger the magnetic field, the stronger is the Zeeman effect. So here's an actual photograph of a spot group, and you put a slit of a spectrometer. So remember in advanced lab, right? You had the slit of the spectrometer. So you didn't, because you didn't take advanced lab yet, but you had the slit of the spectrometer. And you can take a spectrometer and hook it up with a telescope. And instead of having a spectrum tube be what you shine on the slit of the spectrometer, have it be a portion of the sun's surface that you shine, an image of the sun's surface that you shine on the slit of the spectrometer. And that means that the spectrometer will make a spectrum for each little piece of the slit. And here you're seeing the so-called Zeeman splitting. In other words, outside the spots, where there's only a weak magnetic field, here's a single spectral line. But inside the spot region, where there's a strong magnetic field, it's become 3 spectral lines. Right, can you see that? 1 spectral line, 3 spectral lines. Right? The stronger the magnetic field, the further apart those spectral lines become from one another, the bigger the shift in the wavelengths due to the presence of the magnetic fields, messing with the energy levels, if you will. And so this is what allowed Hale to determine that sunspots are magnetic in the first place, that he was seeing the Zeeman effect in the spectrum of the regions around sunspots. And he could use the amount of Zeeman splitting to determine that the magnetic field strength was several thousand Gauss, compared to about half a Gauss or so for Earth's magnetic field. In the sunspots, the magnetic field strengths are like 2,000 to 3,000 Gauss in the umbra. So that splitting of spectral lines tells us that spots are a magnetic phenomenon. It is cool. Yes, correct. What questions do you have?
With the 3 dark lines going up horizontal.
Oh, the horizontal lines are just the spot. In other words, this slit is going through this particular region. So it's darker here. Right? It's just the different parts of the spots where it's darker there. Yeah. I think it doesn't line up perfectly, but that's what it's caused by. It's the spots themselves being darker. What other questions do you have? So here is a photograph of the sun from the Big Bear Solar Observatory, BBSO, on 29 October of 2003, so almost 21 years ago now. And there are some, it was a time near solar maximum like we are now, so there's some big sunspot groups there. Now we can use the Zeeman effect to make what's called a magnetogram of the sun. We can map its magnetic field. And what you do is you use the fact that not only do you cause multiple spectral lines because of the Zeeman effect, but they also, the light from them has different senses of circular polarization depending on the direction of the magnetic field lines, whether they're pointing towards you or away from you. So are you familiar with the idea of polarization of light waves? So, right, you can have, the simplest is plane polarization, where the electric field vibrates up and down in a single plane. But you can also have circular polarization, where instead of the electric field oscillating along, if at any point for plane polarization, the electric field goes back and forth along the line. Circular polarization is the electric field literally makes us, sweeps out a circle, essentially. It rotates around instead. And then there's elliptical polarization, which is in between, where the tip of the electric field vector traces out an ellipse as opposed to a circle. So with the Zeeman effect, those 3 spectral lines have if it's a split that produces 3 spectral lines, the 2 that move away from the center, so to speak, have opposite senses of circular polarization. And so what you can do is take a photograph of the sun through polarizing filters, one that lets through one sense of circular polarized light, another that lets through the other sense of circular polarized light, and subtract them from one another. And now we would do it digitally. They used to do it with photographs, but now we do it digitally. And you can actually map the sun's magnetic field, or really what you're mapping is the component along the line of sight to us. And so I always forget to double check. It's because I don't know why, but anyway, I don't know if it's white corresponds to north polarity, as in taking north to be sticking. If you drew the field lines, the arrows would be away from the sun's surface. South would be towards the sun's surface. I think it's white is north and black is south, right? So in other words, north polarity, south polarity would be the field lines point into the sun, north polarity out of the sun. It doesn't matter really. What's important is that you're seeing opposite polarities there. But the point is, this magnetogram was made at very nearly the same time as the optical light photograph. And what you can clearly see is that sunspots are magnetic regions, right? If I flip back and forth between them. Okay? So there's a little bit of rotation between them because they weren't made at exactly the same time. But notice this one has a particularly simple structure there. Notice that this spot is north polarity and this spot is south polarity, right? And similarly, now this is a more complicated group of spots, and so it's a complicated mess, but you see north and south magnetic polarity in proximity to it. And this gives rise to this idea then of, then that would make sense if there's these magnetic arches that are connecting the spots, because then the magnetic field would be pointing out on one side of the arch and in on the other side of the arch. And so that all makes sense. Here's another thing to notice. So the sun with north up rotates in the same sense that Earth does, west to east. So as the sun rotates, you would see, if you made a movie, you'd see these spots all moving across the sun from left to right. Leader polarity is the polarity that's out in front in the direction of rotation. So this is the leader polarity for this group right here is north. And here's the follower polarity is south for that group. If we look at the white light photograph, this is the leader spot. This is the follower spot for this bipolar spot group. So this is kind of a classic bipolar spot. This is a mess. It's more complicated than that. But simple pairs of spots, even this one's kind of complicated, but overall, a simpler pairing like this is you've got a bipolar spot. Notice that the leader spot tends to be more kind of circular in shape. And the follower spot tends to be more like this. This is associated with the leader spot tends to have more concentrated magnetic flux, and it fans out and produces a more diffuse area of spottedness on the follower spot. If you have a unipolar spot, which you get sometimes, you might just see a single spot like that. What's happened is that the magnetic flux on the follower side is spread out enough that it's just not suppressing convection enough to make spots on that side. So if you look at this carefully, if you look at the magnetogram, what do you notice about leader versus follower polarity when you cross the equator? You go from one side to the other. It's opposite, right? In the northern hemisphere of the sun, geographically speaking, not magnetically speaking, the north polarity is out in front and the south polarity is trailing. But you go into the southern hemisphere and it's the south polarity that's out in front and the north polarity is trailing. Now that's at this time. We're going to shortly talk about the sunspot cycle and the magnetic cycle. The sunspot cycle is about 11 years long, where you go from a maximum in the number of spots to a minimum and then back to a maximum again. The magnetic cycle is twice that because the magnetic polarity overall flips from one sunspot cycle to the next sunspot cycle. So that's a 22-year period for the magnetic cycle. So this was around the time of the sunspot maximum. At the next maximum, the roles would be reversed in that south magnetic polarity would be leading up at the top, north of the equator, and north magnetic polarity would be leading down on the bottom, south of the sun's equator. So you have to flip the flip, so to speak, to get back to the same magnetic polarity. So we say that the sun has an 11-year sunspot cycle and a 22-year magnetic cycle, because the magnetic polarity flips from one cycle to the next. So you have to flip twice to get back to the same original polarity. Kind of like flipping a coin, right? Just like heads, tails, heads. You have to turn it over twice to get back to heads again. Okay? What questions do you have? All right. So remember that magnetic field line points in the direction that the north pole of a little compass needle next to it would point. That's how we defined north and south magnetic polarity when people were discovering that you could make compasses. If you make a little compass needle, which is itself a little bar magnet, by definition, the north pole of the bar magnet is the one which points to the north when you just let it float in the Earth's magnetic field. And the south pole is the one that points to the south. So we can probe a magnetic field by using a compass. The compass needle will line up along the local direction of the field line. And we've just made the convention that the arrow on the field line goes from south to north on the little bar magnet that would line up with it. If the north end of the compass needle, the magnetic field line point, the arrow on the field line goes from the south end of the compass needle to the north end of the compass needle that you're using to map it. And that means, well, you know, if you do that for an actual magnet, well, if you've got a bar magnet, then the magnetic field lines, the arrows point away from north and towards south, because if I had a little bar magnet right here, a little tiny little bar magnet, the south pole of the bar magnet gets attracted to the north pole of the horseshoe magnet and vice versa. So that means that the south pole of the bar magnet would be here, the north pole would be here. So the arrow goes from south by convention, south to north on the bar magnet. So that means that the field lines look like they're flowing out of the north pole and flowing into the south pole. It only is the drawing convention. There's nothing moving, right? Sometimes students get confused by that. There's no motion implied here. It's just the convention on the direction of the magnetic field that it points away from north polarity and towards south polarity. So this is what the magnetic field lines of a horseshoe magnet look like, essentially. And if you have a bar magnet, they look more like this, right? So does that all make sense? It's familiar from, you know, E&M or from second semester, like Physics 111, talking about magnets and stuff like that, right? Okay. Now, we go back to our sunspots again. The idea is that, again, you have this magnetic polarity where there's like south polarity next to north polarity. And so the idea is that with a sunspot group, it looks a lot, there's obviously not literally the case, but it looks a lot like you've got this big horseshoe magnet underneath the solar surface, and the sunspots form at the north and south pole of the horseshoe magnet, and the magnetic field lines connect the two sunspots, and the opposite field polarity arises because then you've got magnetic field lines pointing away from one sunspot, and then you arch around and they point into the other sunspot. So it's a natural kind of explanation of that opposite magnetic polarity, is that the field line looks a lot like the field of a horseshoe magnet under the sun. The spots form on the poles of the magnet, and there are these coronal, we still call them coronal loops of magnetic field lines that connect the two spots to one another. So this is an ultraviolet image that shows hot gas, that shows, what's that? What time is it? It is 5, whatever it says there. 5:26, yes. No, I'm not done. 6. Yes, 6. Why?
So, because I was just gonna try to get you to join the SSR.
Oh, when do we have to?
Well,
But that's,
they
is that,
sorted last week, but
Right.
you know, everyone wasn't there, so.
right, but didn't you say we can do that
Still tomorrow.
tomorrow, right, yeah.
So we
Right.
can do it?
Yeah, I suppose, yes. Uh-huh, yeah. Okay, thank you, dear.
So it's going to be something like 10 minutes at the end of every lunch.
Yes.
Yeah.
So much pressure.
Yeah, but Jules wanted to.
Yes.
But I
of
don't know
course.
what TV was about, I don't know. Because Kyle said
I
I
would-
would join too, but I don't know.
My team,
No, they did a sorting process last week.
Oh, really?
so it was kind of
but
sorted.
oh, here we go. Yeah, you wouldn't even want to be on my team because you just want to beat me, right? Ms. Competitive over there.
Well, no, but if we're on the same team, then I want to win. At the-
Yes, that's right. See, we could win together and then we're
Yeah,
both
but
happy.
that's not sorted.
I don't know. We'll see, won't we? What's that?
That's separate.
I don't know. You get pretty haughty when you win. These wives, I tell you. So anyway, this is an ultraviolet image. And it shows hot coronal gas. So the sun has the photosphere. Above that is the layer called the chromosphere, which is what you see when you see the prominences, the pinkish, right? The chromosphere is pink in color. We'll say more about all this later. Then there's the corona, which is the outer atmosphere, if you will, of the sun. It seems funny to talk about the atmosphere of something which is a big ball of gas, right? But still. This is gas that's like at 1,000,000 Kelvin trapped on the magnetic field lines because it's plasma. And that means that the electric charges will, as we'll again talk about in detail as we go along here, gets trapped on the magnetic field lines. The electrons spiral along them. And so what's beautiful about an image like this is that the hot plasma allows you to literally kind of see, well, you're not seeing the magnetic field lines themselves, but it allows you to say, trace out the magnetic field lines because it's trapped on the field lines. So it's pretty, it's beautiful. And a visible light image would show sunspots at the base of the arches of the coronal loop there. So it's pretty cool, is what it comes down to. So here is the figure from the Astronomy 111 textbook, and we're going to go much beyond this. But then the basic idea is that magnetic fields trap gas, and so that gives you those arches that you can see in those extreme ultraviolet or X-ray images. At the foot points are the spots, which have a temperature of 4,000 to 4,500 Kelvin. It varies a bit from spot to spot. You got the surrounding photosphere. You've got convection within the photosphere, but not inside the spots. And this really isn't drawn to scale because the spots are really bigger than the convective cells inside the photosphere. So that's not really shown here. So I would have changed that about this drawing. But that's the basic idea. What questions do you have? Okay. Oops. So again, here's this idea that electrons, protons and electrons both, and nuclei. Well, really, it'd be not many protons because again, the solar photosphere isn't hot enough to ionize the hydrogen for the most part. But ions of metals in astronomer parlance would be spiraling around magnetic field lines too, but they are much more massive than electrons. The electrons are a lot more mobile. So it's primarily the electrons that are spiraling around the magnetic field lines. Why do they do that? What is the force on an electric charge in a magnetic field? Do you remember? What's the formula for the force on an electric charge in a magnetic field? For an electric charge, it's Q times E, right? Q being the charge. For the electric force, I mean, it's F is equal to Q times E, but there's also a term that involves the charge, the velocity, and the magnetic field to get the force on the charged particles in the magnetic field due to their motion. Well, that would be, it's not quite just QVB. Got to get a little bit fancier than that because it's vectors. QV cross B, right? QV cross B, right? The vector cross product. QV cross B. Yeah, let's see, you're doing the right hand rule. It's good to be left-handed because as a left-hander, I don't have to put down my pencil to do the right hand. No. So the force on a charge QV plus QV cross B. So if we're just considering the magnetic force, we just have QV cross B. All right. So let's reason this out here. Suppose that there's a vertical magnetic field in this room, just this magnetic field lines pointing upwards. Okay. And suppose I've got an electron flying through, moving perpendicular to the magnetic and coming towards you. So B is up, V is this way. Which way is V cross B? So here's B, here's V. So there's two ways to do the right hand rule. There's this one, and then there's I do this one, where I curl my fingers in the direction from the first vector to the second vector. My thumb points in the direction of the cross product. The other one is this. I don't even remember how this one works. I think you look like you're using this one, which is perfectly fine. And I don't remember how, but either way, we're going to get the same result here. So if B is up and V is like this, V cross B points which way? Towards my front or towards my back? B cross B, if I curl from B to B, I'm getting like this. So my back, yes. Right, so V cross B is this away. So for the electron, what direction does QV cross B point? That away, because electrons have what electric charge? Negative. So the electron flying along here has a force in that direction on it. So if the magnetic field is uniform, so, well, okay, let's a couple steps, right? So V cross B is perpendicular to B, right? And therefore perpendicular to the direction of motion. So is the magnetic field doing any work on the electron? You're correct, Scott. It's not, right? Because work is, right, dW is F dot dr, right? Or dW dt, the rate at which work is being done, is F dot dr dt. In other words, force dot velocity. But the force is perpendicular to the velocity. So force dot velocity, if the two vectors are perpendicular, what's the dot product of two vectors that are perpendicular to one? 0. So the magnetic field does no work. So what does that tell you about the speed of the electron? It's kinetic energy. If no work's being done on it, what's true about its kinetic energy? It's constant. Constant, so what's true about its speed? Constant. So the motion is going to be constant speed such that the force is always perpendicular to the velocity. How can you bring that about? Give me an example of motion that's at a constant speed and the force is always perpendicular to the velocity. Yeah, uniform circular motion, an orbit, right? Uniform circular motion. So the electron will execute if you've got a uniform magnetic field, the electron, if it's moving perpendicular to the magnetic field, is going to execute uniform circular motion in the magnetic field. That would be the motion of the electron. Now, suppose that the electron isn't moving perpendicular to the magnetic field. Suppose it's moving at an angle, like this. So the force is QB cross B, but we can resolve, if here's the magnetic field, okay, and here's the electron motion. So let's say this is B, then we can resolve, how I want to do this. Yeah, so I can either resolve along B or resolve along B. This is B just going as I go along here. If I had planned this beforehand. We can think of V as being the sum of B perpendicular plus B parallel, where B parallel is the component parallel to the magnetic field direction, and B perpendicular is the component perpendicular to the magnetic field direction. And so QB parallel B perpendicular plus B parallel cross B will just be QB perpendicular cross B, because what's true about parallel vectors and their cross product? If two vectors are parallel, their cross product is 0, right? So this piece is going to give 0. In other words, there's no force on the electron in the direction of the magnetic field. There's 0 force parallel to the magnetic field direction. Force is only perpendicular to it. So if there's no force parallel to the magnetic field direction, what does that say about the velocity parallel to the magnetic field? If there's no force, what's true about the velocity? It's constant. Yes. So V parallel is constant, and V perpendicular is not constant because it's undergoing uniform circular motion. Its magnitude is constant, but its direction is changing. But V parallel is, as a vector, just plain constant. It's unchanging. So that means that, again, if I've got this uniform magnetic field, if the electron starts out moving perpendicular to the magnetic field, it just executes uniform circular motion. But if it's moving at an angle to the magnetic field, then perpendicular to the magnetic field, it's executing uniform circular motion, but its component of velocity along the magnetic field stays constant. So what does that turn into? Helical motion. Helical motion. That's why the charged particles spiral around the magnetic field. That's what's ultimately going on there. Now, if the magnetic field is not uniform, so that the magnetic field lines are bent, something like this, well, then the motion becomes more complicated, because then the electron speed will stay constant again because no work is being done. But a careful analysis shows that what the electrons end up doing is exchanging energy between kind of their circular motion and their along the field line motion. so that they actually will bounce back and forth from one side of the field to the other. And this is what happens in Earth's magnetic field when you have particles spiraling from the north to the south magnetic poles. It's because the field lines are not all parallel to one another and constant in magnitude. And so in that case, they spiral back and forth. They concentrate along the poles, can crash down and make auroras and stuff like that. It's also the principle for like magnetic bottles for like nuclear fusion reactors and stuff like that. But in any case, for our purposes now, what we want to notice then is by this argument I made, they spiral around the magnetic field lines. So they get trapped on the magnetic field lines, in other words, as a result of that. Ooh, pretty cool, huh? I like it personally, I'm saying, okay? I'm gonna pause because I see Anushka's writing, and I don't want to discourage that by any means, so please continue. What questions do you have? Okay, cool. All righty. Okay, so now let's look at this idea of, we've already noted it, but here's a cartoon of sunspot groups on the sun in the two hemispheres. And so, I should find, this is from a version of the textbook where they messed this figure up. And so I had to use the GIMP, which is similar to Photoshop, in order to doctor it, to fix it, which is why the north and south are not quite the right colors. This figure from that textbook had them backwards, and so I chopped them out and moved them to put the labeling properly, because they had north labeled where the field lines were flowing in and south where they were flowing out, looking to flow out. So sunspot pairs have that north-south dipolarity, if you will. And again, that's a natural consequence of field arches where the field lines would point out on one side and in on the other side. And then the other piece is what's called the Hale polarity law, this notion that the sunspot groups, the polarities are flipped across the two hemispheres. In this case, it's in a magnetic cycle where south polarity is leading in the sun's northern geographic hemisphere, north polarity is leading in the sun's geographic southern hemisphere. And then this is an image of coronal loops again. I think it might even be the same one as before, where we can actually, in ultraviolet and X-ray images, see the magnetic field lines that are connecting the two spots to one another. This is from you always have to have acronyms. And so this is the TRACE spacecraft that took that, where it means Transition Region and Coronal Explorer. The transition region is the region between the chromosphere and the corona, where the temperature starts rapidly rising towards 1 or 2 million Kelvin. And so it's exploring the transition region and the corona. And so it's the TRACE mission as a result of that. And by the way, it lets you trace out magnetic field lines and all that sort of thing. Always there has to be an acronym. It seems to be the rule for these things. This is, again, the ultraviolet images, it's always going to be false color because our eyes can't see ultraviolet. So if you look carefully, this is exactly the same image as this one, just with a different color palette. But again, we want to illustrate that, as we say in technical terms, sun big, right? Because here is the Earth in a true size comparison to those coronal loops, right? They're just gigantic, right? They're much larger than the Earth is. Excuse me. This is an image from the Japanese Yohkoh Soft X-ray Telescope. Soft X-rays means low energy X-rays. Now, there's no such thing as low energy X-rays in the step from the standpoint, they're all much higher energy than, visible light photons are. But certainly longer wavelength X-rays have less energy than shorter wavelength ones do. And so we talk about soft X-rays versus hard X-rays. And the Yoko mission launched by the Japanese contained a soft X-ray telescope that made lots and lots of images of the sun in soft X-rays. And the hot 1,000,000 to 2,000,000 Kelvin coronal gas trapped on these coronal loops shows up beautifully in an image like this. It lets you see the complex magnetic field structure of the sun above the surface. And another cool thing here is, you see that black thing behind everything, right? The black circle, that's the photosphere. In X-rays, the photosphere is dark. And so it's, kind of just the opposite. The photosphere is the dark thing, and then you can see all those coronal loops and so forth in those X-rays. And there's lots of cool movies that were made by Yoko. This is like from the 90s. It shows solar flares, and there's rotation movies and all sorts of cool things, as a matter of fact. So I spent a little time in graduate school. My advisor knows Leon Golub, who's a researcher at the Harvard Smithsonian Center for Astrophysics. And so he sent me to Boston to work with Leon for 6 weeks. And what his specialty is sounding rockets launching X-ray telescopes rather than putting them in orbit. So he would launch these sounding rockets that would observe X-rays in regions that satellites like Yoko, orbiters like Yoko were not covering, so that get complementary images. And one of the missions that he launched failed in that there was a leak. There was a little crack in the plate that was supposed to block visible light from the X-ray telescope. And so the images come back, and there is visible light contamination of the X-ray images. But sometimes there's serendipity, right? Where it's a lucky thing. And so he showed me those images, and I was looking at it, and I noticed that where there were pores, the nice thing about this is then you could see the X-ray image overlaid, if you will, on top of the visible light images. So you could see the sunspots and the coronal loops at the same time. And I noticed that for the pores, there were never any coronal loops with foot points in a pore. They would have foot points in spots, but never in pores, little tiny spots that don't have penumbras. And so I casually mentioned this to him, and he's like, oh my God. And because this hadn't been noticed before, because nobody had ever accidentally made, an image with white light and X-rays at the same time like that. And so we actually published a paper about that, because that was the first time that it had ever been known. So, and so I got like a first author paper out of that just for noticing that. So that was pretty cool. Just a little personal story I thought I'd share with you there. And that has something to say about how the corona is heated. In other words, that's an input into, okay, if pores are not associated with hot coronal loops, then any mechanism heating the coronal loops must not operate in pores, is what it comes down to. So here is a cool movie of a flare and also a coronal mass ejection, because both happen at the same time in this particular. And so you can see the sparking up, if you will, of the so what's happening is you get this complex magnetic field that relaxes to a simpler, lower energy configuration. And remember Faraday's law that says that changing magnetic fields give rise to electric fields? Well, when this happens, you get strong electric fields associated with the rapidly changing magnetic fields that can accelerate particles into space. And so you can get these coronal mass ejections and sprays of high energy protons and electrons and so forth associated with flares. And auroral displays, as we mentioned, because it turns out that it's not the particles coming from the sun that produce the aurora. It actually turns out that the interaction between the magnetic field of the coronal mass ejection and the Earth's magnetic field can cause reconnection in Earth's magnetic field and release energy and accelerate particles that were already trapped in Earth's magnetosphere and cause them to crash down on the north and south polar regions and produce auroral displays, unless there's a really strong CME or a series of them, where this can become a much bigger effect, and it can come down to low latitudes, and why you can see an aurora even down here in Delaware, for example. And so that's what happened recently, was that big sunspot group had a series of CMEs that produce really strong auroral activity. So that's the good point of CMEs. The bad point of CMEs is that they could really mess up civilization. So we'll end today with a video about that. Phil Platt mentioned a 2012 CME that missed us, but that would have caused a lot of damage if it had hit us. Here's a video about that. We're doing things to try to protect our infrastructure from CMEs like this. Probably not enough, and we'll regret it if we haven't done enough, as this video will explain.
Carrington-class CME narrowly misses Earth, presented by science at NASA. In mid-April, scientists, government officials, emergency planners, and others converged on Boulder, Colorado for NOAA's Space Weather Workshop, an annual gathering to discuss the perils and probabilities of solar storms. The current solar cycle is weaker than usual, so you might expect a correspondingly low-key meeting. On the contrary, the halls and meeting rooms were abuzz with excitement about an intense solar storm that narrowly missed Earth. The close shave happened almost 2 years ago. On July 23, 2012, a plasma cloud, or CME, rocketed away from the sun as fast as 3,000 kilometers per second, more than 4 times faster than a typical eruption. The storm tore through Earth orbit, but fortunately, Earth wasn't there. It did, however, hit the Stereo A spacecraft. Researchers have been analyzing the data ever since, and they have concluded that the storm was one of the strongest in recorded history. If it had hit Earth, we would still be picking up the pieces, says Daniel Baker of the University of Colorado, who presented a talk entitled The Major Solar Eruptive Event in July 2012, Defining Extreme Space Weather Scenarios. This storm might have been stronger than the Carrington event itself. The Carrington event of September 1859 was a series of powerful CMEs that hit Earth head-on, sparking northern lights as far south as Tahiti. Intense geomagnetic storms caused global telegraph lines to spark, setting fire to some telegraph offices and disabling the Victorian internet. A similar storm today could have a catastrophic effect on modern power grids and telecommunication networks. According to a study by the National Academy of Sciences, the total economic impact could exceed $2 trillion, or 20 times greater than the costs of a hurricane like Katrina. Multi-ton transformers fried by such a storm could take years to repair and impact national security. A recent paper in Nature Communications, authored by UC Berkeley space physicist Janet G. Luhmann and former postdoc Ying-D Liu, describes what gave the July 2012 storm Carrington-like potency. For one thing, the CME was actually 2 CMEs, separated by only 10 to 15 minutes. This double storm cloud traveled through a region of space that had been cleared out by another CME only 4 days earlier. As a result, the CMEs were not decelerated as much as usual by their transit through the interplanetary medium. Had the eruption occurred just 1 week earlier, the blast site would have been facing Earth rather than off to the side, so it was a relatively narrow escape. When the Carrington event enveloped Earth in the 19th century, Technologies of the day were hardly sensitive to electromagnetic disturbances. Modern society, on the other hand, is deeply dependent on sun-sensitive technologies such as GPS, satellite communications, and the internet. The effect of such a storm on our modern technologies would be tremendous, says Luhmann. During informal discussions at the workshop, Nat Gopalswamy of the Goddard Space Flight Center noted that without NASA's stereo probes, we might never have known the severity of the 2012 superstorm. This shows the value of having space weather buoys located all around the sun. It also highlights the potency of the sun even during so-called quiet times. Many observers have noted that the current solar cycle is weak, perhaps the weakest in 100 years. Clearly, even a weak solar cycle can produce a very strong storm. Says Baker, we need to be prepared. For more information about storms on Earth and among the stars, stay tuned to science.nasa.gov.
So if somebody asks you about your project, you can say, well, we're studying stars. Because in order to better understand solar magnetic fields, we want to compare and contrast the solar magnetic field with magnetic fields on other stars. And star spots as regions of concentrated magnetic field give us a way of doing so. And better understanding the sun's magnetic field can help save civilization by helping prepare for blah, 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 right? So I always, when scientists are asked why about their research, there's a tendency, maybe partly I think it's because the reporters push for this, to give a practical reason why they're doing their research. And that's fine. And, it is true that better understanding star spots can lead to a better understanding by comparing and contrasting of stellar magnetic fields in general and the sun's magnetic field in particular, which could, in principle, help us understand space weather better, et cetera, right? So all that stuff I was saying. So you can, tell people we're trying to save civilization. But I have a problem in that the real reason that we tend to do things is because it's cool and interesting. And I feel like we ought to emphasize that as well and try to get people excited about it simply because it's cool and interesting and not because it has some sort of purported practical application. I don't think that we should always kind of feed into the notion that the only reason to do science is for practical applications. And, as I tell students in 110, 111, if all you try to do is fund science that's going to have practical implications, well, nature is more clever than we are, and you're going to miss out on a lot of valuable practical applications because you're only trying to find valuable practical applications, right? So for example, the Global Positioning Satellite System crucially relies on general relativity, on the fact that gravity affects the rate at which clocks tick. And if you didn't account for that, on the difference in the ticking rate of GPS satellites higher in Earth's gravitational field compared to receivers down on the ground, GPS wouldn't work because the microsecond, the nanosecond differences that produces translate into very measurable errors because the speed of light is a foot per nanosecond. It's a meter every 3 nanoseconds. And when Einstein was trying to figure out general relativity, his motivation wasn't maybe someday this will lead to practical satellite navigation. There weren't even any satellites back then. His motivation was, I want to understand the fundamentals of gravity better. And so you'd have never funded his research if it was, trying to be for practical reasons. And now GPS is this indispensable tool that's worth billions of dollars every year. You just, I'm preaching to the choir here, but you just never know when some pure theoretical research is going to lead to some really practical result that nobody could possibly have imagined beforehand. So, of course, the real reason we're studying star spots is because they're cool, ha 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 ha, sort of, because they are cooler regions on the rest, right? So they're literally kind of like, cool. But on the other hand, there is this practical side to it too, of better understanding stellar magnetic fields actually does have practical implications, because understanding the sun's magnetic field really has real world implications and economic implications for us here on Earth. So we can honestly say also that the kind of research we're doing can have practical applications and maybe even save civilization. Well, that might be a stretch, but still,
That's all the time.
Yeah, What are you doing this summer? Working to save civilization.
Stopping Armageddon.
That's right. That's right. And so you can thank me when, what, did you tell him that, right? Say, you can thank me when society continues to function as a result of my summer project. Yeah, that's right. That's right. Exactly. Yes. Okay, that's our first day. Indeed. I guess I can stop the recording now.
An outlet was off the whole time.
Oh, didn't charge very well then, did it? Whoops.
Charged all.
Oh, no. Did it actually go all the way to